Okay, well, let's get started. I'm Bob Mann. I'm one of the academic leads of the network, and I'll be just introducing the start of our meeting. And this is a discussion about SSA in astronomy, and hence obviously we should start off asking what SSA is and why we think astronomers ought to care about it. An SSA, space situational awareness, also known as space domain awareness, is the study and the understanding and the knowledge of the space environment and the impact that it has on objects in orbit around Earth. And ESA split this up into three aspects: space weather, near-Earth objects, and the third aspect, which is the aspect that we're especially interested in this afternoon, which is the tracking and the study of resident space objects, which are active and inactive satellites and debris that's been generated from them. And there's a lot of it. Here's a plot of the number of RSOs which are being tracked and its evolution over time, and you can see that there are over 20,000 objects over 10 centimeters which are being tracked at the moment. And this is a real mixture of objects, and there's active satellites, inactive ones, and things like their rocket bodies, and about half of the objects are debris. And you'll spot that obviously there's an overall increasing trend in the number of objects, and that the debris numbers increase strongly after discrete orbital events. And these are only the objects which are being tracked, but it's important to understand that in low Earth orbit, and that objects as small as a centimeter are able to end a mission, and there's only estimates about the numbers of those, and indeed the NASA and ESA estimates differ by a factor of 2, and hence actually there's a lot that isn't understood about the orbital objects that are of interest. Okay, well, that's SSA. Why ought astronomers to care about it? And I think there are three reasons. Starting off with is that it's important economically. If you have a look in the National Space Strategy, there's a discussion of the value of the UK space industry and the much higher value of the economic activity that satellites enable, and indeed, obviously, they underpin a lot of aspects of our everyday lives, and hence space is listed as an element of the critical national infrastructure in the UK. And this national space strategy also highlights SDA as a key capability priority in the space area, and an area that actually needs expanded effort. And we'll hear from Katherine later on in the meeting how that expansion actually might happen. So SSA is important economically, and it's an area in which I think astronomy is able to have a real impact. And there's a lot of overlap between SSA and astronomy, in that SSA actually uses the same kinds of data which are used in astronomy. They're captured using the same kinds of instruments as astronomers use, and indeed it can even be astronomy instruments that are used in the SSA observations. And then the analysis of the data overlaps a lot with the kinds of analyses that astronomers do, and hence it's obvious that astronomers have a lot of the skills and expertise and experience that's needed in the SSA area. However, even though there are all of these similarities, equally actually there are some important differences. And obviously, as you'd expect, the SSA data has commercial and often security value that we don't have in astronomy, and hence that hinders the sharing and the integration of SSA data, which is obviously a lot easier in astronomy. And the third reason that I think astronomers ought to be interested in SSA is that at this stage in the evolution of both astronomy and the space industry, it's crucial that we have constructive interaction with them. And the reason this is important is the huge and rapid expansion of the number of satellites in orbit through the advent of these constellations. And it's estimated that at the end of the decade that there will be of order 100,000 active satellites in orbit. And the impact of these on astronomy is obvious. It's especially obvious in these optical images. However, actually, in lots of respects, it's actually harder on radio astronomy than it is on optical astronomy. And hence, I think there's an obvious need to have constructive interaction between astronomy and the space industry, and it's only if we understand each other's priorities and constraints that we can handle this, I think. So these are the reasons that astronomers should care about SSA, and obviously this overlaps strongly with the reasons that we started the GNOSIS network. We started with the first two of these reasons, and the third has obviously expanded in importance over the years that the network has actually been active. And this is a network that's funded by TFC, and its overall aim is to foster interaction between TFC funded researchers and experts from government and industry in the overall area of space debris and the sustainability of the space environment. And the network has funding for 4 years, and this is for establishing and sustaining a community in this area, and for funding some small scale scoping studies and proof of concept projects, and also we are half funding 2 studentships, and you can read about all the details here on the GNOSIS website. And you'll be hearing this afternoon from a lot of the people who are active in organising and leading the network. Don and I are the academic leaders of it. Stuart and Dins bring a whole host of experience in the SSA area from industry and also from the military. The project office of Teresa and James organise everything, and we have a steering board of industry and academic luminaries with an extremely active Kerr, Katherine, who will be speaking in the meeting later on. And our aim then this afternoon is to introduce more astronomers to the overall area of SSA and to GNOSIS as a network that's active in that area, and to discuss some of the future opportunities which would enable astronomers to collaborate and with industry and the government and its agencies in this area. And to that end, then, we'll start off with some introductions, which will be discussing the overlap between SSA and optical and radio astronomy. And then after that, Stuart will highlight a list of the areas in which research effort is needed in SSA, and then we'll have a contributed talk from James Osborn, and then after the break, we'll have a series of talks on aspects of collaboration in the overall SSA area, after which the speakers will join into a panel, and we'll have a discussion at the end of the afternoon with the aim of ending at around 5:30. So that's the end of the introduction, and at this stage I shall then hand over to Paul Chote, who will be speaking about optical astronomy and SSA.
Right, thanks, Bob. Just give me a minute because I'm having a slight technical difficulty. Okay, that's visible? Okay, yeah. Thanks.
That's good.
Right, good afternoon, everyone. My name's Paul Chote. I'm from the University of Warwick. And as Bob said, I'm going to start off the afternoon by giving a little bit of an introduction into the overlap between optical astronomy and SSA. So I'm just going to start off with a little bit of an introduction about myself, then run through a whole list of topics. My kind of goal with this talk was to be more of an introduction rather than a comprehensive review, in the sense that I'm definitely missing some key kind of studies and papers and stuff. And the examples that I've chosen have really been picked based off things that have got nice figures rather than necessarily things that have been top quality science. Yeah. So about me. So my background is astronomy, specifically instrumentation and using that instrumentation to do high cadence, high precision photometry of compact objects, pulsating white dwarfs, CVs, eclipsing binaries, and so on. But for the last few years, I've switched over and have been focusing most of my time on the SDA area. I would be derelict in duty by not saying that I have been taken up GNOSIS on some of the funding opportunities with the proof of concept funding, and also just been awarded one of the part-funded PhD studentships, which I'm currently recruiting for. So why SDA? The kind of cynical arguments are that, well, this is a nice impact case for the Astro group. And it gives us hopefully access to some new funding opportunities, which is good for everyone given the pressure that we're feeling for funding under astronomy. But actually, as we got more into it, we came to realize that this is an important upcoming area that's only going to become more important and more visible over the next few years. And it's not really being addressed. Certainly the stuff that we're interested in hasn't really been addressed properly within the UK yet. And that there are a lot of really interesting research questions that do fit our expertise. And I'm hoping to kind of help nudge some of the audience today to realizing that maybe you can agree on that point. So just to start off, addressing the elephant in the room, I would say the most publicly visible interaction between astronomy and SDA is the doom and gloom of how all the satellites in the sky are going to permanently ruin astronomy forevermore. And this is definitely an issue. And, you know, the cat's out of the bag. All we can do is mitigate. We need to learn a lot more about these satellites and the space environment, and then work out how we can tweak our astronomy instruments and observing protocols to try and minimize the damage. I just put in a couple of plots here from different papers and a screenshot of our own go-to facility being photobombed by Starlink. But, you know, this isn't really what I want to talk about today. There are people in the community, people in the audience even, who know a lot more about this than I do, and I really leave this topic to them. I'm going to talk more about what can astronomers do for SDA. So to start off with, we have access to instruments with big apertures, and that lets us go and look at some of the faintest, hardest to see objects. And, you know, the first challenge to understanding, you know, objects is to find them. And it's very challenging to view these small kind of 10 centimeters, sub 10 centimeter objects, certainly in the geosynchronous regime, where radars can't really reach. And because these things are moving, you can't really use long integrations to find them. So the only way to directly see these things is to do surveys with large apertures. So I've got a couple of examples here from the literature for the last few years. On the right, a very short study that was done using the Magellan telescope. And then our own Warwick study that we did with Dstl on using the Isaac Newton telescope, showing that yes, there is indeed a large population of these very small objects, and pushing things a bit further, that actually a lot of these objects are tumbling. And so that then leads us to question, well, what does it actually mean? Can you really say that something is 10 centimeters based off kind of a spherical cow approximation, if that 20th magnitude measurement is actually something that's varying between 21st magnitude and 16th magnitude on a very short time scale? At the other end of the kind of instrumentation scale, you can also use astronomy instrumentation with very small apertures. They also have a very special place. So what I've got here are two instruments that were designed for exoplanet surveys. Mascara on the right is an all-sky camera, and SuperWasp on the left. And so, you know, the idea behind exoplanet search is that you want to have very wide field of view that can do very precise photometry. And those two properties are very useful for looking at light curves of low Earth orbit objects in the optical. And yeah, there's quite a few interesting papers out there on doing that, including one of my own. And so, yeah, that's one thing. But then what can we do? So the easiest thing, particularly at GEO, is we just take a whole bunch of measurements. We can say, well, we know where everything is. Let's fit orbits to these. And at GEO, again, where radar is not very good, optical measurements are the primary means of doing this. But this isn't something I really want to talk about today, because this is more astrodynamics than astronomy. The kind of, we can get the data, we can get very good data using our instrumentation, but then that kind of gets handed off, and all the interesting fun stuff is done by the astrodynamicists. And there's a bit of a kind of cross collaboration, terminology, culture barrier there that I think will be addressed in some of the later talks. So I'm going to kind of draw a line under that and leave that here. So, well, with one exception. So another kind of interesting thing, and the first area where we kind of really directly look at techniques rather than just instrumentation, is the surveys for near Earth objects. We want to try and look for very faint moving objects. The only difference really is the timescales. Whereas a kind of near Earth asteroid might be moving, a few pixels per hour on your image, say, whereas something at GEO may be moving a few pixels per second. And so it becomes quite difficult in both cases to look for deep objects, because you can't just integrate longer. And so something that was done first with the NEO surveys, and which is now an active topic of research in the SDA community, is this idea of blind stacking. So you take multiple short images, where in this case short is on the time scale of your kind of motion. So for NEOs it might be a few minutes, whereas for say LEO observations you're talking small fractions of a second. And then you stack them all together, shift them at different velocities, and out pop hopefully faint targets that you don't see previously in a single frame. And this is something that we have actually also done a little bit of work on, leveraging the INT survey that I showed a couple of slides earlier, where we have direct observations with a 2.5 meter aperture to find these really faint, uncatalogued debris. At the same time, we had a small 30 centimeter class telescope slaved to the INT, pointing at the same patches of sky. And so we could apply these blind stacking techniques, or in this case, it's really semi-blind, because we already knew an object, we knew where to look, and we knew to plus or minus a couple of percent its velocity. And sure enough, we can recover these objects that are completely not visible in individual frames, and find an improvement of 2 magnitudes or so, which is quite significant. Getting down to 19th magnitude with a 36 centimeter telescope is pretty good. The other topic, which obviously astronomers understand a lot about, is light curves. So looking at the brightness of objects and how they change over time. So on this slide, I'm giving some examples of derelict geosynchronous satellites that have been pushed up into graveyard orbits. And then under the influence of solar radiation and gravitational perturbations, they all generally start to tumble with different periods. And the shape of these tumble light curves, well, first off, yeah, so you can, you get a light curve. Many of these are periodic. You can work out what the period of the tumbling is, and then you can phase fold them, which is what I'm showing here. And so you can see in these top 4, these are all Gorizont satellites that look something like this. And you can see that their phase folded light curves are very different to these HS376 type spinning cylinder satellites. And also the periods are quite different. But also these periods aren't constant. So all of these spacecraft are under the influence of these perturbative forces. And one of them, which is particularly interesting, is the Yorp effect, Yarkovsky-O'Keefe. I can't pronounce the rest of it. Everyone calls it Yorp, where you have thermal radiation being absorbed by typically a very non-uniform shape, and then re-emitted at certain orientations that then impart torques. And so over timescales of weeks to years, you can see quite dramatic changes in the attitude state of different satellites. Particularly interesting example of this was the GOES-8 satellite, which are the plots below, where Aljuba et al. Were able to model this quite well and show that over time, the period was lengthening. And then they predicted that it would enter a non-uniform tumbling state, which indeed happened. And so the paper on the right shows kind of an update from that, where they saw that, yep, the period increased and then it started tumbling. So that's a nice example of kind of predictive power at work. Another kind of somewhat of an aside is you can use the light curves to directly detect changes in the operational state of a satellite. So this is Intelsat 29E, which some people might remember had an anomaly a few years ago. So this panel here on the top right is showing the light curve composited from several days from survey observations that we took. And this is a very kind of typical light curve that you'd expect from a 3-axis stabilized geostationary communication satellite. Fairly boring, changes over the course of the night under the influence of the apparent relative motion of the sun. And then on the bottom left, I'm showing a movie from the ExoAnalytics, who have a lot of telescopes monitoring a lot of the geobelt. And you can see that from the start, I'll wait for the video to get back to the start. That this object has a sudden flash, and then shortly afterwards expels a lot of its fuel. And then at some time later, you can actually see other small faint objects moving away from it. So this had a rather energetic anomaly that caused it to eject all of its fuel and other pieces of debris. And so after that, light curve observations that we took showed that, yes, this is now in fact tumbling at quite a rapid rate. And the rate of tumbling was changing from day to day. And in fact, this sharp transition between the nights of the 18th and the 19th corresponds to when the company declared it a total loss. So we can kind of infer that something must have happened that caused them to, or coinciding with them saying, well, this is it, we can't do anything else. Another really fun, more quantitative example is the AGSI experimental geodetic satellite, which was launched in the mid-80s by JAXA, which is a 2-meter diameter sphere with mirrors and retroreflectors, which is spin stabilized. And the idea was to be able to use laser ranging and optical ranging to be able to measure very precisely positions and distances on the ground. But it also makes it a very useful test case and validation case for SDA capabilities. And so this plot I'm showing, this top left panel is showing the orientation of mirrors that was measured experimentally by a group using satellite laser ranging measurements. But actually, we can use those plus our optical light curve measurements and basically correlate the individual flashes that we see, which correspond to the groups of 3 mirrors in each of these latitude bands, to each of these groups is aligned with unique separations between them, such that you see, when you see a group like this, you can uniquely match that to one of these rows, and that gives you what the latitude of the kind of reflecting bisector is. And you can match that then across the entire light curve as it passes overhead and get an optical measurement directly of what the spin axis of this object is. This is a nice simple example, but in principle, this can be expanded out to basically anything. If we have a sufficiently detailed model and a sufficiently constraining light curve, you know, we can in principle back out things such as the orientation of the satellite spacecraft and also information about its material properties and what it's doing. Going from LEO in the previous case up to GEO, something which is done a lot in the SDA area is looking at light curves of stabilized geostationary objects over the course of a night, which are called typically phase light curves. And what this is showing here is you've got time along the x-axis, but rather than being strictly like UTC time, it becomes a lot more convenient to measure it as effectively the distance between the object and the anti-solar point, because you have the illumination geometry of the sun, the satellite, and the observer has a longitudinal component as well as time. And so by plotting against the solar phase angle, everything lines up on different satellites a lot better than if you were just doing time. Whereas on the y-axis, we have, as astronomers will be familiar with, a calibrated magnitude scale, which is generally measured relative to the background stars as they move through the frame. And you can immediately see here that this is showing off simultaneous light curves of 6 objects that are all grouped quite closely together on the sky. And we can see immediately that even within one night, there is a lot of differences between, in fact, all of the satellites. And at a qualitative level, we can link that back to inferring information about what they are. So for example, we know that this magenta one down the bottom, which is Meteosat 11, is one of these cylindrical spinning satellites. And so it doesn't have many distinguishing features that change with angle, so it has a relatively flat uniform brightness over the course of the night. Whereas the other 5 are all box-wing satellites. And so you get these big specular peaks that correspond to when the angle of the solar panels against the sun coincides with the observer on the Earth. But even then, we can see that this blue one, which is Intelsat 1002, is quite different from the others, which all have their peaks around 0 phase angle. This one is offset by about 30 degrees, and it's also double peaked. One thing I should mention is that this gap at around 0 phase angle corresponds to, because these things are all above the equator, and this was taken almost right on the equinox, the sun position is at 0 latitude, and so the Earth's shadow sweeps across the geostationary ring, and everything gets blanked out for about an hour every night. So we can tell for Intelsat that not only is its solar panels offset by about 15 degrees relative to the sun, but also that the north and south solar panels are offset by a few degrees relative to each other. Then you have these other features around here, which you can see on this yellow, which is 4.6, and also some of these other features like this green one on 4.7 that correspond to reflections of features of the satellite body itself. And so even at a qualitative level, we can start to infer things about what these satellites are made up of and the geometries of the features on their surfaces. Another fun thing is that these satellites are not stationary in the sky, they maneuver. And an extreme example of this was the Mission Extension Vehicle 2 satellite, which was in fact the main target of these observations, which was flying about in close proximity to Intelsat 1002 before eventually docking with it. And as part of the Phantom Echoes project, we had access, in addition to all of this fantastic light curve data that I was able to collect, also truth data from the operator of the satellite. And so on the right, I'm plotting with a very simple sketch, an indication of what the orientation of the satellite was doing over a 180-degree roll maneuver. And we can see quite clearly, as you would hope and expect, that as this thing does this roll, and even qualitatively, you can just see that the relative area to the observer decreases, that yes, in fact, we do see a reduction by about a factor of 10 in the brightness, which then returns back to where it was. But a really important thing to note here is that these kind of events happen over very short timescales, a few seconds to a few minutes. And so to be able to constrain things at this level, and particularly to model it, you do need very high quality, very fast cadence observations. And so you can have these nightly phase light curves, but then you have a second degree of freedom that reveals even more information over time. And that is, as over the course of the year, the latitude of the sun relative to the satellites and the Earth change. And each night you're tracing out effectively a different latitude component of each of these satellites. And so if you build up a long enough time series, you can effectively build a two-dimensional fingerprint of the optical signatures of these objects. And then that gives you a lot more information that you can model and use to understand what these things look like and what they're doing. And so I've put a couple of examples here of some groups that have been working on actually modeling, rather than just saying qualitatively, actually modeling what some of these features look like. And in general, this is a very difficult thing to do, because these, the models, you're really limited to relatively simple shapes with relatively simple material properties, because we simply don't know enough about the material properties at the fidelity that you need to capture all the details. But you can still do a pretty good job. So this example on the left, where they were modeling a tumbling LEO satellite, and you can see, okay, the brightnesses don't really match up yet, but they can at least get, at a qualitative level, quite a nice match. Whereas the example on the right, which is modeling one of these phase light curves, you can do even better than that and actually start to extract information about the different contributions of the satellite bus versus the different antenna. And if you read the paper, you can see that actually, to be able to make this model work, they actually need to model a station keeping maneuver happening partway through the night, which is quite an interesting result. So, of course, brightness versus time is one very useful axis, but it's not the only one that we have access to. We can also look at how things change as a function of wavelength. And at the most crude level, you can do that with broadband color photometry. And this is something else that many groups have been starting to look at over the last few years. And even at the simple kind of color diagram level, you can start to separate out different groups of objects and try to understand if you can distinguish between different types of, say, satellite buses, i.e. different materials that are being used, different solar panel construction techniques, but also the effect of weathering and aging of the materials, which then change color as they degrade over time. So that's kind of over the longer time scales, but over shorter time scales, you can also start to see very interesting results. So this example on the left is showing effectively simultaneous multicolor photometry of a phase curve of a satellite. And like I was showing on this example back here, being able to distinguish out reflected components off different parts, that becomes even more constraining when you have access to color information, because different components of the satellites might have different colors. And so we can expect that we may start to see changes in color over time that we can more strongly constrain and be more confident about our models. Whereas the example on the right shows that for a tumbling rocket body, you get these periodic signatures as its orientation is regularly changing, but actually you see slightly different features and different depths of dips in different color bands. And we can use that to, in principle, work out which end, if you say that, okay, one dip corresponds to the front, one dip corresponds to the back, we can actually use this to say, well, this dip might correspond to the rocket nozzle end, whereas the other dip lets us correspond to the top end where the satellite was attached. And that helps break some of the degeneracies in our models. But this is all still very early on, and there's a lot of scope for research, particularly in terms of increasing the quality of the photometry that go into these models, as well as the models themselves. And I think astronomers in particular have a lot to offer in this area. And in fact, this is what my PhD project will be starting to look at. So if anyone finds this interesting and is interested in the PhD, please talk to me. The lad there. Okay, so if we take that to its limit, spectroscopy is even more rich in detail, but is a lot harder. So at the kind of more broader qualitative end, you can do basically higher resolution, multicolor things and look in more detail about aging effects on the right, where we can see for the same class of rocket body that were launched over a time span of 10 years, we can see color changes that we can infer due to aging effects. Whereas the example on the top left is showing the different spectral characteristics of two different classes of satellites. The one on the bottom, I think, is the most interesting. So this was an example, 2020 SO, of an object that was first discovered and thought to be a near-Earth asteroid, but was only later, once they observed its orbit for sufficiently long, realized that no, it must actually be a man-made object. And they matched it to, I believe, one of the rockets used for the Sojourner missions. And so this group did spectroscopy of the object. And by looking at some of the absorption lines, they are able to show that actually this corresponds to the chemical signature of polyvinyl fluoride, which definitively shows that, yes, this object is definitely man-made, and kind of puts that claim to rest as being truth. Another aspect that we can use just to make the most of our optical information is the polarization states. And this is something that is kind of very, very rough, let's say, in the SDA literature. And which, with the types of instrumentation and analysis that come from the astronomy side, I think there's room for significant advances. So, these objects are covered in man-made materials that have different reflection properties, a lot of flat surfaces. So the light that we see reflected off them contains a lot of polarization components. And in principle, the polarization can tell us not just about the materials, but also provide additional constraints on the angles of flat reflecting surfaces. So the panel at the top is just showing some examples of changes in polarization. These kind of dips in the top are real features, not not kind of bad data points, but it's relatively low cadence polarimetry. Things will get much more interesting when going to higher cadences, which is what I'm showing at the bottom from a project I've been involved with, using the new polarimeter on the Liverpool telescope. Whereas on the right, top right, is an interesting model. Well, it's lab-based in that they built an actual scale model of a satellite with realistic materials, and then measured the polarization as a function of angle, masking out different parts of the satellite, and are able to show that, yes, the satellite bus has very different polarization properties to the solar panels. And in principle, if we can then map these to what are seen in real objects, we can hopefully begin to constrain more information about them. Okay, I'm cheating a bit here. So going past the optical into the infrared, there's a lot of interesting material properties and material changes that happen in the kind of 1 to 2 micron region. And so some of the infrared instrumentation and techniques that we have from the astronomy side have potential to do really interesting things. So an example up here is showing differences, being able to distinguish between different solar panel materials, just based on this transition between the Y and the J bands. Whereas at the bottom, is showing off observations actually taken during the daytime, because in the infrared, the sky background gets fainter, and yeah, you can actually, in principle, start to observe some of these things during the daytime, which then dramatically increases, especially for low Earth orbit objects, the amount of time that we have available to get useful observations. And finally, on the kind of instrumentation side, something that I think is really cool and wished I could do, but does require rather specialized instrumentation, is adaptive optics, directly imaging satellites, particularly at LEO. So the two examples on the left are taken by the 3.5 meter Amos telescope on that the US Air Force have in Hawaii. You can see in the top left, the Hubble Space Telescope. We've got the main body of it with the front cover here and the solar panels out the side. And I believe this is the CSAT, which are then sharpened up using some of these multi-frame blind deconvolution techniques. Whereas the example on the right is showing that you don't actually need to have that level of equipment. This was a 1 meter class telescope done by a group at ANU. So even on the academic side, we can, in principle, start to do some interesting things in this area as well. And then finally, on the kind of the data processing side, astronomers are known for big data and fancy machine learning techniques. And a lot of this expertise and techniques can translate directly over into the SDA area, particularly as we start to go to these newer generations of detectors that have extremely high data rates. And there's a growing explosion of data that you just cannot process with human input. So some of these machine learning techniques have extreme promise, but this is still a very active area of research. So I've just included a few examples here of machine learning directly on images to search for streaks corresponding to LEO objects and images, looking at changes in orbits and being able to work out the types of maneuvers that are being done. And then on the right is an example of looking at light curves and using that to try and identify the type of satellite bus, i.e. the shape, all of which show very promising results. So yeah, that's all I wanted to cover. Does anyone have any questions?
Thank you, Paul. That was an excellent introduction. Are there any questions? If you'd like to put your hands up and I can call you in turn. Are there any questions?
So I can't actually see the Zoom window, so
There's
someone would have to.
Hand up from Stuart. Stuart.
Hi, Paul. Very nice presentation. Thank you very much. Was intrigued by your comments about infrared in the daytime, and share your view that, you know, if we can make it work, it'll improve our timeliness of tracking considerably. Are those infrared techniques viable for higher altitude stuff? You said that it would work for low Earth orbit, but can we see geosynchronous satellites in the infrared too?
So it really just comes down to a question of brightness. I think you definitely can see stuff at geo, but it's a lot harder because they're typically several magnitudes fainter than LEO. But if you have, you know, the right instrumentation, small enough pixels, large enough aperture, short enough integration time, you definitely can see the big things. Yeah, the question is it cost effective and useful enough? Is the extra information that you get, you know, I think that remains to be seen. Given how easy and cheap it is to get a wide field, small aperture system that can observe, you know, several hundred objects a night. Yeah, I don't know. That's a good question. And
the question was prompted by the fact that a lot of the optical companies like ExoAnalytic talk about the gap of roughly 6 hours around local noon that they have when they're doing their optical observations, and I was wondering whether, you know, you could switch over to the infrared for that period to maintain custody, for example. But yeah, thanks.
So I guess my cynical view would be to say, hopefully that the tracking that they have from the other 18 hours should be good enough that there shouldn't be a custody issue, but rather that for the smaller number of cases, for things that you expect might be doing sneaky maneuvers, you definitely could, I would say.
Yeah, I think that's the particular application. You know, we've seen quite a lot of proximity operations taking place, sometimes deliberately, as you mentioned with the MEVs, but you know, the non-cooperative ones, I think, are causing concern, and you know, a 6 hour window potentially is enough time for somebody to do something untoward, I think. So
yeah, well, I'd say that almost necessarily the types of instrumentation to do these daytime observations is generally going to be quite small field of view.
Yeah.
So single object should be fine, but I think it's probably unrealistic to have a kind of large area mini object general survey for these things.
Cheers, Paul. Thanks.
Thank you both. I think there aren't any other hands, which means thank you again, Paul, and we should move on to Timon as our next speaker, who will introduce radio astronomy and SSA.
Hello, how's that? Can you see the screen okay?
That's good, Simon, thanks.
Thank you very much. Hello, well, thanks for the invitation to talk at this group. I'm Simon Garrington. I'm one of the Associate Directors of JBCA at Jodrell Bank Observatory, part of University of Manchester. I'm also the Director of the Merlin facility of telescopes, which we'll say a bit more about shortly. This is a fairly new field for me, so I'll try and give a broad overview, and I make no guarantee that it's complete. I'm not covering you know, the work done by dedicated radar facilities. I'm trying to focus on how, you know, radio astronomy facilities can be brought in to add some value to some of the SSA work. I think there's two main themes. There's sort of active work using radar, and then passive measurements, either passive radar or using the signals broadcast by satellites themselves. Both both have got a long history. I thought it'd be entertaining to look back at some of those historical connections in a couple of minutes. But it's also fair to say that despite an early start, nowhere near as much work has been done in general, on the radio astronomy side in this field compared to the optical. So I think there's potential, and we'll look at some of the capabilities and hopefully find some areas where we can do further work. And I'll certainly show some of the recent stuff that we've been doing in this area. So just to go back to some of those historical points, I mean, they go right back to the very early days of radio astronomy, because radio astronomy developed, from the inventions of radar and other navigation techniques during the war. So the sun was first detected at radio wavelengths during an investigation of radar jamming in 1942. Meteor echoes were first detected when JSA was looking for echoes from V2 rockets, and the first discrete sources, the first radio galaxy Cygnus A, detected using the same equipment in 1946. And the very first experiments done at Jodrell Bank, before they built any telescopes, radio telescopes, before the field of radio astronomy even existed, was to do radar observations of meteors. And the first use of the big dish at Jodrell, the 250 foot, was to detect Sputnik, rather the carrier rocket, the ICBM that launched Sputnik in October 1957, using 36 megahertz radar, and you can see the individual sort of pulse returns at the bottom there. At the same time, the Cambridge group were using interferometers and Doppler trapping on the Sputnik signal to measure its orbit and even deduce atmospheric drag. And of course, the defence counterparts and colleagues of Lovell and Ryle were doing their own work in parallel, and also made radar and passive detections. And it's interesting, of course, that work didn't get anywhere near the sort of press attention that the involvement of Jodrell Bank and Cambridge did in those early days. But interesting that it's worth just pursuing that sort of dual use in terms of defence use of some of these facilities. The dual use of the big dish at Jodrell was raised during its construction, but there was never any military component to the funding. But nonetheless, that suggestion that it might be used at shorter wavelengths for missile tracking had a huge impact on the design and the capability of the telescope. And without that motivation, the telescope wouldn't have had anywhere near the impact that it has had in astronomy. So that's interesting. And in fact, just for a bit of entertainment, just pursue this question of the link between SSA and ballistic missile warning. Our primary facility in the UK, now Fylingdales is used in a dual way for both missile warning and space debris observations. And the forerunner of that, the US ballistic missile early warning system was commissioned in 1958, and the UK involvement was agreed in 1960, but wasn't operational for a few years after that. So those discussions on the use of Jodrell Bank for missile warning started in mid-1958, about a year after the telescope was built. In 1961, the RAF Signals Command installed radar transmitters and display screens, actually sort of Army sort of war surplus, fairly low-cost equipment. And in secret, in 1962, RAF radar operators were trained at Jodrell Bank, mostly on satellite observations. And it's interesting, I spent some time at the National Archive unearthing some of this stuff. It's interesting to read some of the reports and where they talk about a signal to noise of 1 for a radar cross-section of 2 square meters being a practical lower limit. It's rather worrying to think that people might be making the sort of decisions that they might be making on the basis of a signal to noise of 1. It was very low tech. Just a sort of, visual A scan, just a horizontal scan of a range, and some of the reports talk about a simple abacus to compute the threat level and that this would be relayed via a dedicated phone line to fighter command. And there's a huge reluctance to spend any money. They only spent about £6,000 on equipment compared to the £10 million that was invested in by the UK in Findingdales, and the £2 million per year to operate Findingdales in the UK. And yet, interestingly, this was all the UK had during the Cuba Missile Crisis, and the actual use of the deployment of the telescope during that tense period in October 1962 is another story, I guess, which we'll save for another time. So all that radar interest and effort, it means that there was and there is a well-developed field of radar astronomy. Going back to the first detections of the moon and the development of synthetic aperture radar independently for astronomy use in making lunar images. You see an example there on the top. The race to get the first echoes from Venus, and hence the distance of Venus, and calibrating the astronomical unit in the late 50s and early 60s, and then the rotation rate of Venus from sort of Doppler CW studies, then detections of Mercury, Mars, Jupiter followed fairly quickly and developed into the whole field of detailed planetary radar imaging, which is mostly now done by static radar with Goldstone and Arecibo when it was available, and the Greenbank telescope and the VLA as an array being the receivers. And that's now been extended, obviously, to much smaller bodies, near-Earth objects, Earth-crossing asteroids, and so on, and leads to the dedicated space debris radar facilities such as Haystack, MIT Lincoln Lab, or JPL. So it's just worth, I'm not going to talk much about the dedicated radar facilities. I'm more interested in how we can use the radio astronomy facilities that we have. So just a quick sort of summary of the range of telescopes and facilities that are available. We have large single dishes, the sort of 100-meter class dishes in the US and in Germany. Our own 76-meter dish here at Jodrell, 64-meter dish in fairly new dish in Sardinia. Obviously, the much larger 305-meter dish in Arecibo, before it collapsed, was designed for both radar and astronomy use. But then we have arrays of telescopes at sort of centimeter wavelengths, ranging from, say, a 35-kilometer size array, DLA in the US. In the UK, we have a 200-kilometer array, E. Merlin, and then on European and global scales, telescopes around across the planet collaborate to produce arrays up to the size of the planet, and they really provide our high-resolution radio imaging, the precision astrometry and positional measurements, and I'll talk about that later. Then there are the lower frequency meter wave arrays. Generally have much wider fields of view, able to scan the whole sky electronically. So that's LOFAR in the Netherlands and in Europe, and the MWA in Australia. And the common capabilities of these radio astronomy facilities that they all have high sensitivity wideband receivers. They have flexible digital backends, including the capability to sample the raw voltage across quite a wide band. They're very well synchronized, either having sort of independent hydrogen maser frequency standards or dedicated synchronization systems. And that means we can also refer things to proper astronomical reference frames, such as ICRF and so on. So a natural sort of use then is to think of using a dedicated radar transmitter and a large radio telescope to gain sensitivity as the receiver in a bistatic setup. So examples of that have been done in Germany using the Tira transmitter and the 100-meter Effelsberg telescope as the receiver, and that bistatic combination then allowed the sort of threshold for debris detection to be pushed down to the sub-centimeter level. There's a combination of facilities in Italy also used of this, using either the sort of array, cross array in Medicina, or the Sardinia 64-meter as the receiver. So that's sort of, those have been done to sort of do mostly beam park type experiments, just to characterize the debris population. An alternative approach is to do passive radar. So the low frequency arrays, so LOFAR, MWA, SKA low in future, have very wide fields of view. So with electronic steering, so no moving parts, just arrays of sort of dipole antennas phased up. But their frequency ranges enable them to take advantage of powerful sort of illuminators of opportunity, whether that's FM or digital audio or digital TV transmissions. And so those can be complementary to these narrow beam park surveys that some of the dedicated radar facilities such as Haystack and Goldstone have done. So the NWA in Australia have succeeded in detecting a range of satellites, from big things like ISS to small satellites needing debris, using passive radar in the FM band, and now developing coherent processing to push the detection threshold further down. LOFAR, mostly the Polish group actually using the Polish LOFAR stations, are developing passive detection using digital audio as the illuminator of opportunity. They've got reflections from aircraft for sure, and have done simulations for how that might be applied to LEO objects. And it's a similar setup to the French Graves surveillance radar, which is a bistatic UHF setup, but it's again using an opportunistic illumination, but a larger receiving array. So quite complementary to that technique. So some of the work that we've been involved in is to push this bistatic radar to longer baselines. That's been coordinated via a NATO sort of sponsored group led by Marco Martorella at Pisa in Italy. So we're mostly using L-band, so 1.3 gigahertz, and the transmitters are at MIT Lincoln Lab, Haystack in the US, or the Tira transmitter near Bonn in Germany. And there's the receiving side. We're using the biggest radio telescopes that we can get our hands on, so the big dish at Jodrell, and the smaller Merlin telescopes, or the Sardinia 64 meter, and the Westerbork telescope in the Netherlands. And mostly this is looking at geo targets where you need the high sensitivity because of the distance, and they're also easier for these larger, slower radio telescopes to track. But they're proved to be quite tricky to coordinate and analyze. The radar facilities are generally optimized for monostatic operations where they have complete knowledge of the transmit waveform, and the synchronization is fairly straightforward. Also, they're quite different communities, the radar community and the radio astronomy community. So trying to get them to use common data formats and scheduling and everything, all the usual things can be a challenge. I'm quite keen to promote the use of a standard VLBI data format used by all most of the telescopes around the world that participate in long baseline interferometry. Because that then allows the potential fusion of a radar experiment like this and radio astronomy. That means we can synchronize properly, we can calibrate the propagation delays, we can align things to very precisely to celestial reference frames and so on, and allows us to maximize the advantages of these long baseline bistatic experiments where we can do robust multistatic solutions for positions of objects. So just a couple of slides on the very first results from some of these experiments, which involve MIT Lincoln Labs, the Millstone Hill radar in the US, Dstl in the UK, various sort of astronomical partners, us at Jodrell Bank, Astron in the Netherlands, INAF in Italy, so on. So using the Millstone Hill radar transmitter, MIT, and Westerbork and Sardinia as the receivers, then MIT have processed the data, the sort of coherent pulse compression, techniques on some larger geo targets and had got successful detections, calculated ranges, velocities, and so on, as you might expect. Looks like, as you might think, that the biostatic radar cross-section can be less than the monostatic. Maybe that's sort of what you expect for typical satellite configurations. And then with TIRA in Germany transmitting and our network of telescopes, eMerlin in the UK receiving, then I've processed these data just using incoherent FFT techniques, and we've got detections at multiple eMerlin antennas, and Dstl have looked at these data and confirmed this as well. And now with haystack transmitting and using eMerlin in the UK, we've now got detections at multiple antennas there again, so far just using incoherent processing, and we'll build up to the coherent processing of that. And then also Goonhilly are involved in some of this work, and they've done an experiment with a closer transmitter, a CW, just using the sort of carrier of a communications transmission by Airbus to get a detection of some geo satellites too. So it was quite a struggle to pick out these very faint signals. I spent a long time poring over these data. So just to show you some of the signals that we get, we can see trains of individual pulses, which was quite a surprise given the estimates of the sensitivity. And then Dstl have done some more processing and sort of looking at the average pulse by doing an overlapped FFT analysis. So I think there's a lot of promise in using some of these techniques. Duncan Murray at Dstl has looked at whether we can do a multilateration solution then using the relative delays of the received signal to the antenna spread across the UK, because they're accurately synchronized in principle at the sub-nanosecond down to the picosecond level. So we can measure those relative delays accurately and use that for orbit determination. So Duncan's been doing looking at the algorithms for that solution and some simulations for how that might work. And then I wanted to move on to a sort of different approach. So there's a whole sort of field of using global networks of telescopes for precise positioning observations of celestial objects, mostly distant quasars, now coordinated by the IVS, the International VLBI Service. And those global VLBI measurements define our celestial reference frame at the sub-milliarc second level, and they measure telescope positions at the millimeter level. So you can use those to study plate tectonics, glacial rebound, measure the orientation of the Earth very precisely, length of day variations, polar wobble, etc. And then you can, over smaller fields of view, you can do relative astrometry, either to those or a secondary grid of calibrators at the micro-arc second level. So radio astronomy does allow these very precise positioning measurements, and it's natural to think how that can be extended to spacecraft and satellites. So if I start with the more distant objects, obviously NASA and ESA and their deep space networks of large dishes observe satellite or spacecraft beacons using techniques such as delta differential one-way ranging, so where you're doing sort of double difference of delays between different telescopes and between spacecraft and celestial sources to get precisions at the sort of 100-meter level at distances of 1 AU. And there's a very nice radio astronomy implementation of that type of technique called PRIDE, developed at JIVE. That uses global network of telescopes, uses the sort of phase referencing technique and multiple secondary calibrators, and then that reaches 50-meter precision at 1.5 AU. So fantastically precise positioning is possible, and that's being used to It was used to track the Huygens lander through the atmosphere of Titan, for example. It will be part of the JUICE mission. It's been used for the Mars Express and Venus missions. And then similar techniques used by the Chinese VLBI network to do, say, positioning of the lunar rover at 1 meter precision with respect to the lander, measured from the Earth. So you can think of how that might be applied to satellites too. Again, this allows very high precision measurement. So the whole sort of sphere of space geodesy brings together radio VLBI observations of quasars with GPS observations or satellite laser ranging. And one tricky problem is how you actually tie those techniques together. And one way is to try to do that on the ground, to tie the positions of your ground sensors together. But another way is to do radio VLBI observations of satellites themselves and do what's called a space tie. So that means you want to determine by radio astronomy type observations the positions of satellites at the centimeter level, and potentially link all these different techniques then. So various tests of that have been done on GPS and GLONASS satellites, or the APOD satellite, which combines various sensors and allows that to be done. And simulations being done for future satellites which could have VLBI type beacons on them and the new VLBI observing antennas, and that could work at the sub-centimeter level. So that obviously requires a very careful and detailed understanding of all the delays that contribute to the measurements you're making, and that's all interesting. So I've been looking at a lower precision approach using our network of telescopes. So in this case, I just point the telescope straight up and turn all the fancy delay calibration off, and then just watch. In this case, these are all the GNSS satellites, so GPS, Baidu, Galileo, even some geo satellites, which are the vertical lines in this plot. So this is delay across the bottom and time up the side. So you just see all these satellites sweeping through the side lobes of our telescopes in delay space. So this is the delay measured with the cross correlation of the signals between two of the satellites. So you can clearly separate all these different satellites. Those are the lines of the TLE predictions. Can clearly separate those satellites and measure the delays to meters or possibly even centimeter levels. And that means you can think about how you might use lower gain antennas for this approach and observing multiple satellites. And this is similar to some of the commercial approaches that outfits like Kratos and GMV are doing. But you could also think of recorrelating the data using a delay model to increase the bandwidth where feasible and get higher precision. But we're also able to, in principle, to take advantage of the very precise synchronization that we have between antennas. So in principle, that could allow much more precise delay measurements and much more precise positioning to be done, and take advantage of the whole infrastructure and sort of correlation processing that we have in place for these arrays of telescopes. And that's related to some work I've been doing on sort of terrestrial and airborne sources, how you can observe these artificial signals and do the correlation to measure the delays, and then do direct solutions for the positions using various minimization techniques. So we should also mention the threat and the impact of these new constellations of satellites. As Bob mentioned at the beginning, there's a potential for 100,000 or more of these low Earth orbit internet satellites, and their downlinks in the 10 gigahertz band are certainly a significant concern for radio astronomy, especially for the SKA, as well as their optical reflections being a concern for optical astronomers. And there's obviously, as Bob mentioned, several motivations there for having improved orbits and for characterizing their radio transmissions. So some sort of passive radio positioning using their downlinks would be would be very interesting to pursue. Some other groups are already turning this around and looking at the navigation, the navigation on the ground potential for using these as signals of opportunity. And that's an interesting aspect too. So we've started with a low cost sort of shoebox size antenna, which is the small thing at the bottom right of that picture with the big dish in the background, just using a sort of semi-cylindrical reflector and low cost satellite low noise amplifiers. And that's what you see at the bottom with Starlink satellites going overhead every 30 seconds or so, and then the plots on the right show how that signal is distributed in the band, and how also the Starlink satellites have these very narrow carriers in the middle, which can be used for, might just be able to see in the picture there, sort of Doppler shift as they sweep across. So we can use those for sort of Doppler measurements too. So there's certainly potential for doing that, and we're keen to deploy receivers on our network of telescopes to understand, to make these positional measurements, and also to understand the impact, the ongoing impact of these satellites on arrays of telescopes. So I think that's pretty much what I wanted to say. Radio astronomy techniques and telescopes have been used for SSA type observations since the days of Sputnik. The potential and sort of demonstrations for bistatic radar using large sensitive radio telescopes, and that ranges from sub-centimeter debris observations all the way through to large assets at GEO. There are national and global arrays of telescopes that we can use for this, which are well synchronized, well calibrated, and so on. There are techniques of passive radar at low frequencies, either using FM or DAB transmissions or TV transmissions. So arrays like MWA, LOFAR, SKA, low and future all have very powerful capabilities for that sort of work. And then there are passive RF observations using the signals transmitted by the satellites themselves. There are precision applications, such as looking at GNSS satellites to do space ties. There are surveillance modes using lower gain antennas. As I said, there's commercial outfits such as Kratos and GMV doing that sort of thing already. And just to point out that in the UK, we have a unique asset in eMerlin, and that it's a network of sensitive dishes connected by 100 gigabit data links with picosecond synchronization and a flexible real-time correlation system to process the data, so that we can consider sort of fusion observations with astronomical calibration. And we're currently upgrading those digital systems and part of the aim for that is to improve support for future SSA observations. So it's certainly a new field for us. I'm just starting to dip my toe in this field, and we're keen to collaborate with SSA experts and some of you in the audience today. So thanks.
Thank you indeed. Are there any questions for Simon? Any hands appearing? I can ask one to start with. I was interested in the passive radar. I mean, obviously, as you described, that hinges on opportunistic illumination, but otherwise, is it able to happen as you do ordinary astronomy observations? Is this just extra data that you can extract out of other observations?
Possibly. So, your astronomical observations may otherwise try to exclude the FM band where these strong signals are. Right. So that's one aspect, and I think some of these techniques then you want a sort of dual channel. So you want one channel which is receiving your FM signal directly, and then one which is looking at the radar signal.
I see.
But you're right. An advantage of those sort of passive radar observations, they're almost sort of conventional radio astronomy imaging. And so you can literally, make images of the sky and see the reflections of various space objects, which is different from those sort of delay observations that I was talking about, where
Right.
you can't necessarily do a conventional imaging observation.
Okay, thank you. And Stuart has a hand up now.
Thank you, Simon, for a very interesting presentation. With my astronomical hat on, I'm dead keen to ask you about how much the observations of Venus improved our knowledge of the astronomical unit, but I think I should stick to SSA. So my question on that subject is, have you looked at all at generating images of spacecraft in the RF domain using inverse synthetic aperture radar techniques at all?
No, I think I did mention at the beginning that I didn't cover that. So facilities like TIRA and also MIT Lincoln Labs, so they do this synthetic aperture radar imaging of objects in space, and there are some beautiful images, a bit like some of the images we saw towards the end of Paul's talk. So yes, you can do that sort of sub-meter resolution, centimeter resolution imaging of objects using SAR, and that's usually done in the monostatic case. Whether there's an advantage to trying that in a bistatic case to use a larger receiving antenna and get more signal to noise might be worth thinking about.
Thank you.
There's another hand up. Andrew Williams has a hand up.
Hi there, Simon. Thanks for the nice presentation. I just was wondering about your thoughts on, with respect to the Leo constellations, how we can essentially offer the radio astronomy facilities to them as a kind of form of partnership, to encourage further collaboration. I mean, is that essentially the sort of theme of what you were saying?
Not necessarily. I wasn't necessarily offering our data to them, just saying that it would be very useful for us to have improved orbits and improved characterization of the radio signals. I think but another aspect, as you were asking that question, what occurred to me is something that's in the current Ofcom consultation, actually, which recognizes that it will be necessary to use ground-based radio facilities to characterize the signals from these new constellations and to characterize their impact on radio astronomy. So whereas in the past there were a few, one or two dedicated independent facilities that could make observations of signals from satellites and say whether they were or were not complying with ITU standards, for example, there's really not access to those facilities now. So it will be up to us as the radio astronomy community to make our own measurements, to make our case, which is would be nice to get some funding from Ofcom to help with that.
And there's another hand up from Mark Sargent.
Hi, Simon. In a similar vein, maybe wondering about services radio astronomy could provide. I was thinking about the scenario when maybe some satellites would want to one would want to deorbit them by rendezvousing them and taking them out of orbit. And the thought there is, such high precision positioning information, could that be fed back to startups, say, or agencies thinking about deorbiting to fine-tune the final approach to grab the satellite and pull it down? Is that at all thinkable? And could that be a potential use of this?
Yeah, I think any more precise data is valuable. So that so far the motivations for those precise measurements have been quite particular in this issue of sort of frame ties for precision space geodesy. But I think, as you say, there are a lot more practical applications of those sort of precision measurements. Yeah.
Great. Well, thank you again, Simon. And I think we should move on. Our next speaker is Stuart Eaves on the hard problems of SSA.
Are you seeing my screen?
Not yet. Still not yet.
Can you hear me?
Yes. Yeah, we can hear you well, Stuart. Yeah.
That's a step in the right direction.
It is.
I have to admit, my PowerPoint does seem to be sulking slightly. There we go. How about
that's
that?
Better.
All
yeah,
right.
That's up now. That's fine.
Okay. So thank you very much, Bob. I was asked to reprise a presentation that I did a little while ago, trying to characterize some of the challenges that we face in SSA. I think some of those have been alluded to in Bob's introduction and in the couple of talks that we've already had. But I think the general premise of this presentation is that there are quite a number of areas where at the moment we're probably not doing a sufficiently good job to achieve a sort of capability that we might refer to as space traffic control, and that there are quite a number of different types of measurement that we might wish to make that would make that situation better. So this is a summary of the capability gaps that we've put together with input from various people in the GNOSIS community over the last couple of years. So this is just a summary list, and what I'll do in the next few slides is to talk to each of these particular issues in a little more detail to try and give a sense of the sorts of things that I think we probably need to try and achieve via whatever techniques are available to actually improve our knowledge of the environment in Earth orbit. So one of the concerns that satellite operators have is that even objects down to about 1 centimeter in size have the potential to cause significant damage to satellites that are operational. An object of 1 centimeter in size traveling at 7.5 kilometers a second has a comparable energy to a hand grenade, and you can imagine that, you know, letting off a hand grenade next to a satellite isn't likely to improve its performance. As Bob mentioned in the introduction, one of the major uncertainties that we have is how many objects of this sort of size range there actually are. NASA and ESA have differing models for the consequences of hypervelocity collisions in space, and so have quite differing estimates of the number of objects in this size range. And it may be the case, slightly depressingly, that some people are concerned about getting even smaller objects. I saw a presentation by a member of the insurance community recently who is particularly concerned about sort of 0.5 centimeter sized objects, just because the expected population of 0.5 centimeter sized objects is even greater. It's, you know, measured in millions, and even though such objects might not completely disable a spacecraft, they might degrade its performance sufficiently to the point that the insurance industry has to pay out, at which point, you know, it becomes an even harder problem. And one of the frustrations that I have is that the uncertainty in the knowledge of the population size means that it's very hard to get a coherent answer if you ask some of the experts in the field, you know, are we approaching or past the Kessler threshold density for, you know, chain reactions of collisions in space at certain altitudes? And it's very hard to actually give a decent answer to that question at the moment. Another issue that we have is that if we do end up with a catalogue that incorporates all of those very small objects that we think are up there. The system that we have at the moment really probably doesn't have sufficient sort of capacity and measurement frequency to actually maintain proper custody of all of those objects. If you just look at the sort of very practical issues, most satellite orbits are reported around the world in a 2-line element set, which is a fixed format description of an orbit devised by the US in the early days of the space program. And there just simply aren't enough decimal places in some of the fields to accommodate very large numbers of objects, and the sort of degree of precision that can now be achieved, you know, even if we are able to do the sort of things that Paul and Simon were talking about, making sort of centimetric accuracy measurements of objects in space, a 2-line element set doesn't have enough decimal places to get to centimetric accuracy. So we have some challenges in terms of building a much more comprehensive database rather than just a set of 2-line element sets for objects in order to understand their positions. And when we get to these very large catalogue sizes, the challenge of doing the conjunction analysis will get progressively more difficult. The number of conjunctions goes as n squared. So if you have a much larger n as your number of objects in your catalogue, you can see that n squared progressively more challenging over time. We've had some references already to some of the historical facilities that were put in place during the Cold War, with concerns about ballistic missiles heading over the pole towards the UK and to the United States and Canada. So the major radars that the US developed at that time, which are based in Greenland and Alaska and here in the UK at Fylingdales, are clearly at reasonably high latitudes for a very good reason. And a lot of the optical facilities that the US has access to are much further south than the equator, with the result that things in low Earth orbit tend to spend almost half their time while they're over the southern hemisphere out of range of the tracking network that we have available at the moment. So one of the ways to try and improve the general quality of the knowledge of objects is to track objects more frequently. And if for half their time we're not tracking objects, you can see that there is the potential for them to you know, sort of change orbit and their positions to become more uncertain. And we'd like to improve the cadence with which we actually track objects as they move around the globe. We've already had some references to the degree of accuracy that we might wish to achieve, but one of the sort of examples that I saw presented a little while ago was somebody saying, well, we had this conjunction warning. It said that a debris object was going to pass within 50 meters of our active satellite with an uncertainty of plus or minus 1 kilometer. And as you can see, you know, that sort of level of uncertainty is really not helping us to understand whether we need to actually make evasion maneuvers with our satellites. We need to try and find techniques to reduce the size of the error ellipsoids around objects and then keep them small. But it would certainly help to make, you know, sort of very precise measurements from time to time to actually give ourselves a good starting point for an orbit propagation. But that's not the whole challenge. We also need to understand the various perturbations that apply to satellite orbits and debris orbits to a higher degree than perhaps we do at the moment. And that is moving our modelling from a current sort of situation, which has been characterised by a gentleman called Marie Bajar from the US, who's one of the leading lights in the US SSA community, as treating everything like cannonballs, i.e., you know, there's an assumption that you're propagating a spherical object forward in time, and there are, you know, clearly not all the objects in space are cannonballs. In fact, very few of them are, you know, like the calibration sphere that was shown earlier. A lot of them have unusual shapes, and if we want to do a better job of propagating their orbits forward, we need to start taking that sort of thing into account, because what we would like to do is to move the capability to a point in the future where we can extend the reliable forward prediction of orbits beyond the 2 to 3 days that we can do at the moment. And the reason for that is to give operators more time to actually assess the potential collision risk, to actually get better, higher accuracy data on the objects potentially involved in the conjunction, and then actually make a much more informed decision about whether to maneuver or not. We still have some challenges associated with maintaining custody of objects. You know, we make observations with telescopes and radars. We get usually an intensity measurement back. That intensity has obviously got a temporal component to it. We've seen some light curves already today. But in general, knowing what it is that's reflecting the energy back to the sensor is not something that we do especially well. And we need to get a better understanding, especially for a number of the debris objects. You know, what size and shape are they? Their future orbit evolution will depend on their ballistic coefficient, their area to mass ratio. And that's particularly important when it comes to making predictions of their re-entry. One of the standard products that comes out of the space tracking and control community is estimates of re-entry, but they are hampered by a lack of knowledge of the parameters of objects. At certain points when the drag gets particularly significant, you'll find that an object will cease to rotate and will adopt a sort of shuttlecock-like attitude, and the point at which that happens is directly related to where it will ultimately re-enter. So we need to understand some of these parameters much better. The objects that we observe, as you'll have seen from some of the presentations earlier, have time variant signatures because they spin and tumble. This is important information, not only for you know, the sort of re-entry calculations that I was talking about earlier, but if you think about the problem that was alluded to in one of the questions just now, which is you know, going up and doing debris removal. If you had a debris removal satellite, how would you choose which target objects to go and remove? Well, obviously you might try and work out which ones would create the biggest mess if they collide. And some analysis has been done to suggest that some of the large rocket bodies that are in orbit at the moment might be some of the better objects to get out, because they constitute quite a lot of mass that could generate a lot of fragments if they were to collide. But after you've got a sort of class of objects in mind, you then have some more subtle considerations that you need to think about in regards to, you know, how well do we understand the object that we would be going to try and get hold of, and arguably an object that is stable or is spinning around a constant axis is potentially much easier to grab than something that's tumbling with a motion that's on more than one axis. And so having that knowledge would allow debris removal companies to plan their operations much better. As we discussed talking about Paul's presentation earlier, there are quite significant limitations in the optical domain during daytime. Now, you might think that, well, if you can't see them optically in the daytime, then we could use radars instead. And that's certainly true for certain objects, but there are a category of objects in Earth orbit, probably largely composed of bits of thermal blanketing that have peeled off spacecraft in the past, which we know are up there and we've seen optically, but we can't see with radars. They appear to be non-radar reflective, and essentially the radars look straight through them, which gives us a problem because we now know that our catalogue is somewhat incomplete. And the inverse problem applies with the optical community. There are certain objects that are very dark and potentially quite difficult to see in the optical because they don't reflect very much sunlight. There may be some potential in the areas that Paul was talking about using the infrared, because any object in Earth orbit is going to be kept well above absolute zero by the Earth's albedo and the solar illumination that it receives. So anything in Earth orbit is going to have some sort of infrared signature, but we need to develop the networks to actually provide tracking for those objects that are challenging targets in one domain or the other. Paul touched on the issue of materials, and at the moment we're still not very good at understanding the effect of the space environment on materials. There have been a few experiments. The one illustrated here, I think, was associated with either the shuttle or the long duration exposure facility, which was a test mission that the US left in orbit for a while. But there are a number of physical processes that take place. Some of them involve atomic oxygen at the top of the atmosphere, which combines with the materials for things in relatively low orbits. There are effects associated with the ultraviolet light that falls on materials. And as you can see, they potentially change color and change even their physical configuration as they start to sort of delaminate and curl up. And all of these things will affect the way that we try and track them. Paul showed some examples of rocket bodies changing their apparent optical characteristics over time. Another technology that definitely changes in spectral characteristics are solar panels. And you can see those changing in their spectral characteristics over time too. One of the interesting challenges that we've discovered through campaigns to try and keep track of satellites using novel technologies like ion thrusters is that any satellite that's operating a thruster for extended periods of time, which ion thrusters tend to do because they're very low thrust, high efficiency maneuvering units, becomes a particular problem for the space tracking community, because essentially the tracking community at the moment makes the assumption that they track an object and that they are modeling all the major forces associated with that object. But if it's operating a low thrust ion propulsion unit, you can see that there's a major force term that's affecting the subsequent evolution of the satellite's orbit that is not being taken into account. And experiments with the Northrop Grumman mission extension vehicles that were heading up to GEO demonstrated that it is quite hard to keep track of some of these objects, which is one of the reasons why I think operators of satellites with these sorts of propulsion systems are going to have to get a lot more cooperative with the space tracking network if they're actually using these sorts of technologies, because only they know when the unit is switched on or not. We have a big challenge in understanding whether satellites are operational or not. There may be techniques that we can use, you know, sort of looking at things like whether the temperature of a satellite appears to be controlled, or whether it's just fluctuating in accordance with the illumination cycles. But unless satellites are transmitting, and you know, some satellites quite deliberately choose not to transmit when they're in certain parts of over certain parts of the globe, it's quite difficult to tell the difference between active and passive at times. And that is important, because if they are involved in a conjunction, you really need to know whether they're liable to maneuver and try and get out of the way, or whether you're going to have to take the initiative because the thing that's coming towards you is inert, and it's going to be your initiative to actually avoid the conjunction happening. We could do with much better measurements of space weather. One of the reasons for that is that satellite operations can be affected by the amount of space weather that's going on, and the number of single event upsets that the satellite onboard computers might be subjected to. But one of the things that I feel we probably need to do is to try and not just measure current space weather with on-orbit sensors, but also try to get ourselves to the position where we can forecast what space weather will be a few days ahead, because especially for low Earth orbit objects, understanding how the space weather is interacting with the upper atmosphere and changing the drag on satellites is an important part of figuring out where those satellites will be. We need to get a better capability to model the drag forward in time. There's a somewhat of a crossover with the natural environment in the case of micrometeorites as well. We know that our satellites get hit by very small fragments of man-made stuff. They definitely also get hit by micrometeorites. Even with experiments like the LDEF mission that I mentioned earlier, and other hardware that's been retrieved, like the solar panels from the Hubble Space Telescope when they were replaced. So they've been exposed to the space environment for an extended period, but even with sophisticated electron microscopes, it's actually quite hard to tell the difference between impacts from natural objects and impacts from man-made stuff. And we would like to try and understand, you know, sort of how much of the problem is actually very small debris from a man-made operations. There are differences of opinion about how many very tiny sort of sub-millimeter particles there are in orbit as a result of man-made activities. Some arguments say that based on breakup models, there should be very, very large numbers. But then other arguments say that, well, when objects are that small, their ballistic coefficients allow the solar radiation pressure to make their orbits elliptical quite quickly. And as a result of that, they re-enter in timescales of weeks to months, rather than staying in orbit for years and years like the larger objects do. And to actually resolve this, I'm encouraged to learn that ESA are planning a mission to actually deploy a satellite with a large sort of sail on it, with the aim of actually trying to make some measurements of what the fluxes of objects actually are. And finally, we have a limited ability to monitor satellite transmissions. Certainly in the commercial and open source world, that's true. There are some capabilities to monitor satellite transmissions in the military domain, but for fairly obvious reasons, the military find it a bit challenging to share some of that information. But as Simon's presentation sort of made clear, understanding what satellites are transmitting when, at what frequencies, for how long, with what signal strengths, etc., is going to be really important if we're going to have any sort of chance of understanding and then mitigating the effect of those transmissions on the world of radio astronomy. So we need to get better in that domain as well. So as I hope I've indicated, there are lots of ways that I think we need to improve space situation awareness or space domain awareness. Encouragingly, there are people trying to make the situation better, and commercial operators are starting to collaborate more. So we're moving in the right direction. We think it's going to get harder because we think that especially military satellites are going to spend more time trying to limit their signatures. I've included a picture on the right of a satellite employing what I refer to as SSA warfare techniques, i.e. stealth. If you can't see the satellite, it proves it's working, doesn't it? But I think that's one of the sort of challenges that we're going to face, is that, you know, from a space tracking point of view, we would like to understand where things are better. Both the radio and optical communities might like satellites to be generally harder to see because it would make their life easier, but that doesn't improve the world for the people who are trying to keep the satellites safe, because they'd like to be able to find it easier to track everything. And I don't think I really need to belabor this slide, because I think these points have already been made by Simon and Paul, that, you know, there's a significant potential overlap here between the interests of the optical and radio astronomy communities and what the satellite folks are trying to achieve with these mega constellations that they're launching. So I hope that I haven't depressed you too much. I think there's a lot of potential for us to do better. I think the problem is going to continue to get harder. Satellites will get more difficult to see. I think some people are suggesting that they're already taking steps in that direction. And I think the bottom line is we need to invest more in sensors and processing techniques to make the situation better. And at that point, I'll stop. And if there are any questions before the break, I'm happy to take them. Thanks very much.
Thank you, Stuart. Are there any questions? There's a discussion in the chat about meteors. I don't know if those discussing it would like.
Yeah, if I could just comment, I'm just looking at them. I know Mike Hapgood kindly put the original comment in. So there was a period, I think it was probably on the order of 20, 25 years ago, I don't recall exactly, where there was a predicted Leonid meteor shower that was expected to be particularly intense. And I know that a number of satellite operators actually tried to turn their satellite solar arrays edge on to the expected direction of the flux to try and minimize the potential risk of an impact. And, you know, having that sort of understanding potentially would be very valuable.
Okay, thank you. John has a hand up.
Oh, sorry, I'll put my microphone on as well. Yeah, there was talk about the dangers from sub-centimetre and millimetre scale debris. I was just wondering, do we know what the area to mass ratio of the really tiny debris is? In other words, is it rather flat or angular, in the sense that, like, the Yorp effect or the Yarkovsky effect could actually deorbit it? In other words, could there be a process actually happening which would make the population of such small debris actually not as bad as we think, or not? I mean, I'm not saying it is.
Apologies if I didn't make that clear, but I went to a session at the Royal Astronomical Society on this subject. I think Robert Massey may have helped to coordinate it, and maybe he can recall better than I can, but I think there was a presentation from somebody at the European Space Agency, which what they tried to do was compare orbital lifetimes of objects at different size scales. So they started with a 700-kilometer orbit from memory, and they indicated that, you know, a large satellite that's sort of like 10 meters or something across potentially stays up for, you know, sort of hundreds of years. And then if you come down in size to a 1 meter object, it would potentially be up there for decades. And they came down in size scales, and the time frame that they associated with millimeter sized objects, because of the differences in ballistic coefficient, were sort of measured in weeks to months, which leads you to think that, you know, there might be a sort of peak in the number distribution for debris. It would increase up to, you know, very large numbers around 1 centimeter perhaps, but then because the solar radiation pressure is helping us, it may be that the numbers fall off quite rapidly as you get down to the millimeter sized objects. But at the moment, our ability to actually measure that sort of stuff is quite limited, because obviously it's so small that, you know, telescopes and radars on the ground really struggle to see it. And so ESA has an initiative. I'm not sure if they've given it a name yet, but there is a program to actually deploy something that looks rather like one of the deorbit drag sails on a satellite with some sensors, and then fly it around in low Earth orbit to actually try and make a direct in situ measurement of exactly how many times it gets hit.
Okay, thanks.
Thank you. Are there any other questions? As we were behind schedule, I think we should move on to our next speaker, James Osborn, who's going to speak about his work at Durham.
Yeah, hello. Thanks for that. Can you see my screen?
Yeah, that's fine, James.
Excellent, perfect. So yes, thank you for the opportunity to present my work here today. My name is James Osborn from Durham University. And really my background is in astronomical instrumentation, but like a few others, I've recently started working more on space surveillance and tracking, partly because it's an interesting problem, as Stuart has just described. There's lots of interesting things still to solve. And I think in the optical, that's one of my background and my experiences, so I know more about that than the radio, but in the optical, I think that there is some capabilities that we have in astronomy that could really be quite useful in SSA, and the other way around, in fact, which is why I'm calling it knowledge exchange, because I think it goes both ways. So as a bit of background for those that don't know, Durham University in the northeast of England, in the Centre for Advanced Instrumentation, we have 2 sites. It's quite a large group. So we've got sort of research in the city itself, and then some AIT labs out of town a bit. There's about 70 people in all. And we cover lots of different areas of mainly optical instrumentation, actually. But the ones that really are important for today, I think, is astronomical adaptive optics, free space optics, and space science groups. And we sort of combine them all really to come up with space situational awareness. So first of all, I suppose the audience here is a mix between the space industry or space academics as well as astronomy. So I'm going to introduce a few of the concepts on both sides. We've already spoken a bit about adaptive optics, so I've got a fair bit of experience in astronomical adaptive optics. Here's a photo from the Very Large Telescope in Chile with its 4 laser guide stars, which are probing the Earth's atmosphere. And the reason they probe the Earth's atmosphere is because when we look at stars through the Earth's atmosphere, they appear blurred, right? They appear to twinkle. We can all see that with our naked eye. And that's what's shown on the center image there, this nebula with the blurred out spots. But we turn on these adaptive optic systems, and suddenly we increase the sharpness of these images, so we can extract a lot more information from them. And actually, this photo here is brilliant because one of those little people at the bottom there is me, just for scale. So being there for the first light of this system is really incredible. And this has led on to lots of experimentation with lasers, okay, which, as we know, satellite laser ranging is also important for space tracking, satellite tracking. So something we've worked on recently is with a company called LumiSpace. I don't know if they're here today, but adaptive optics technology can be used to improve precision of larger objects, or even to track smaller objects, excuse me. and perhaps even enable regular daytime operation. Because if you think about it, if you can illuminate something with a laser beam, then we can use a small notch filter in order to separate that from the sky background, assuming that it's bright enough. So from our side, we do a lot of the laser guide star technology from astronomy into the satellite laser ranging with LumiSpace. We also do a lot of the modeling of that, which helps us to design these systems and make sure that they perform optimally. So the little animations there is with and without adaptive optics. So you can see the spot on and so the left-hand one, which is all broken up into small speckles. That is what a laser beam looks like at LEO. Okay, and you can see that it's broken, speckled, and it moves around a bit. So if you're looking for a return in there of a satellite that's, I don't know, let's say 2 meters by 2 meters, you're going to, at some points you'll get high return, at some points you get no return. So if we're thinking about trying to get photometry out of that as well, then we have a problem there. And then on the right, you can see what happens if we turn on our laser guide star system. Okay, it's still wobbling around a bit and it still changes in focus a little bit, but you can see it's considerably better. And actually that wobbling around, that's something that we can improve as well with different ideas. So this is just for illustration really. And the plot on the right there shows the return photons with and without adaptive optics. So without is in blue and then with is in the orange color with the number of photons per pulse on the x-axis. And the next thing I'd like to talk about very quickly is turbulence forecast. So if we're talking about optical instrumentation, anything where we're talking about precise observations has to battle with the turbulence in the same way that astronomical adaptive optics systems do. So using turbulence forecasts that we currently use in astronomy in order to make sure that our most sensitive observations are done in the calmest conditions, or to design our instrumentation for a particular site, that can all be done with SST as well. So the image on the bottom right, for example, is the expected turbulence strength over Europe. In this case, orange is weaker turbulence and the bluer colors are stronger turbulence. So if you were designing, for example, an SLR network, this will help us decide where to put them and then how well they will perform. Okay. Another quick example, again, touching on things which have already been discussed today by Paul earlier, I think. Another obvious application of astronomical experience is in data analysis. So astronomical image analysis techniques can be used for blind detection of low signal noise ratio signals, and even separate different artifacts given any known priors that we might have. We know something about the objects that we're looking at. We know how they move relative to the stars or from hot pixels, for example. And that will give us information that we can use either in in standard analytical techniques or even machine learning techniques as well. So as an example in the images here, here's an image of 3 geo satellites actually, and a few artifacts that look like geos that need to be picked out as well. And a low signal to noise LEO image as well in the center there. You can see that you can see it by eye, but trying to design an algorithm to get this in a robust way, you can see how that's tricky. And just as an example, the image on the right is something we'd see on a wavefront sensor for our adaptive optic systems. And you can see actually it's kind of similar, right? We're looking for these little blobs that move around a bit, and they change in intensity as well in the same way that we might expect satellites to change as they tumble. The other thing that we are thinking about quite seriously is wide field optical imaging, which I know has already been discussed as well. So if we can do this, then we get SST at scale, right? Which means that we get to detect lots of these objects. And this involves a lot of astronomy data analysis techniques as well to identify signals, as I've already said, and potentially moving it into daytime would be very good as well to increase scale as well as custody of these objects. But when we do this, if we look at the models, right, then it works quite well at nighttime, okay, for some hours at least before the objects go into the shadow of the Earth and then we can't see them. But during the daytime, the signal noise ratio is so low that generally it's quite difficult to detect them. And that's where new data analysis techniques are going to be really useful. Something we're actively working on. And this is where I call it knowledge exchange, because it's going 2 ways. Okay, if we have this wide field imager that's picking out LEO constellations as they move across the sky, then it's not such a leap to think, well, okay, we can use this. If we put one at an observatory, then we can use it as an early warning system to project intercepts of bright satellites, low altitude satellites, as they cross or will cross astronomical fields. And that can be used to either avoid, if we can plan well in advance, but that's unlikely with these things moving across the whole sky in a few minutes. We could shutter them, and we can post-process them if we know they're going to be there as well. That gives us that prior, which lets us extract information from our science images. And remember that the satellite crossing time over a telescope field of view is milliseconds, really, and less than a second, certainly. So shuttering it is much more beneficial than throwing away an hour-long observations. This is really quite an important thing to try and do. And we've all seen images like this, right? Okay, so I think we have to say that these images aren't really of a usual case. Okay, in this case, for example, it was I think it was soon after launch for the Starlink satellites. So they're all quite close together and at very low altitude. They're not reached their final altitude yet. So we wouldn't expect this to be a normal case, but it certainly does happen. And this is something which we're very concerned about in the astronomical community. But if we take on these SST type techniques into astronomy, then we can start thinking about monitoring and maintaining a database of the brightness. And that enables us to improve prediction, for example, of how it's going to affect all these different instruments and telescopes, which will all be affected differently. It also gives us quantifiable evidence for the effect of the satellite constellation on telescopes and indeed the night sky in general. And I think that's important as well, because currently we show pictures like this, it's all over the media, and people panic and they shout about it on Twitter or whatever, but it's very difficult to find actually numbers of quantifying this effect on astronomy. And I think that's quite an important thing to do, to inform the policy and policing. Even if we're talking about regulation, then we need to have policing of that regulation in the monitoring and feed into the decision-making process as well. And that feeds into the last point that I want to talk about really, which is AstroSat, which is a software that we prepared in collaboration between Durham University and NORSS, who I think we'll be talking later today. And this is a way of taking the TLEs of satellite orbits and projecting them onto wherever you're going to be pointing your telescope and looking, and then it'll project any satellite crossings of your particular field of view. And combining this with the wide field imaging enables us to validate the predictions. It enables us to make this database of satellite brightnesses, to improve the models. At the moment, the models are all very crude, as already been spoken about. And that enables us to do some sort of satellite mitigation as well, at least for the optical regime. One last thing that we are thinking a lot about in Durham is space situational awareness and space sustainability. So we have a project in Durham where we're really starting to think about a holistic approach to responsible space exploitation. So SST that we're talking about today, that's only one part of this, okay? But that's the technology part, the sensors. Feed that into space track management, space weather, okay, which has been mentioned as well, orbital dynamics, and tying it together with the regulation side, policy, international relations, and such, which allows us to make regulations which have to be monitored. So this is circular, right, which feeds back to the satellite surveillance and tracking. But really, when people generally talk about space sustainability, they're really talking about how much stuff we can put up there without it crashing in order to increase capacity and capability. But what we also need to do is realize that is intimately linked with what's going on in the ground as well. So with Earth environmental sustainability of the supply chain, or even in terms of global healthcare and education. So it's this sort of holistic approach between space sustainability, situational awareness, monitoring, as well as Earth environmental sustainability. It's all linked, and we want to bring that all together. Okay. So there's a very brief summary of what we're trying to do up in Durham. We have a large astronomy group and a large astronomical instrumentation group, which works with adaptive optics, next generation adaptive optics for the extremely large telescope, for example, including solar adaptive optics, so with experience in the daytime as well. We do a lot of optical turbulence forecasting, monitoring, and optical modeling as well, which helps us to understand how instruments will behave and how to locate them and how to schedule observations as well. Experience in machine learning and data analysis, and that all feeds into the SST side in terms of satellite laser ranging, satellite illumination as well, hopefully leading to 24-hour tracking capability. And then the wide field imaging, which is useful for tracking at scale, but also for satellite mitigation for optical astronomy. Now, as I say, we're quite new to all this as well, like many others. So we are keen to collaborate on any interesting instrumentation problems. I think this is why so many people are starting to get involved, because the problems are quite interesting, and I think it's something that we can have a real effect on, right, and see some real world impact, which is particularly good for those of us in academia. Okay, well, that's an extremely quick overview, but thank you for your attention.
Thank you, James. And we have time, I think, for just one question, if anyone has one for James. And there's a hand up from Robert.
Thanks, James. Just to say, I wholeheartedly agree that gathering actual real data on the issues of the impact of satellites in the sky is really important, because we've got some fantastic models, but the more real data there is, the better. So sorry, it's a comment rather than a question. Great.
Yes, I agree with you as well then.
Great.
Thanks.
Thank you. So us, we are a little behind schedule. I think actually we'll reduce the length of our break a little, and we'll restart at 3:30, if that's okay. Okay, and we'll see you then. Okay, everyone, I think we should start again. The rest of this afternoon is about collaboration in the SSA area, and the opportunities and the range of collaborations on offer amongst the various actors in this space. And we'll start off with Katherine Courtney, who's the chair of the GNOSIS steering board and has been one of the leaders of a UK Space Agency sponsored study that's been having a look into the UK's expertise in the SSA area and the areas that actually need extra attention. So, Katherine.
Thanks, Bob, and hello, everyone. I'm going to probably try and catch us up a bit on time, as that study report hasn't been published yet. So there's sort of limited things that can be said about it, but it was a study into the space domain awareness landscape that was commissioned by the space agency, and they were specifically interested in looking at capabilities across industry and academia, and getting recommendations, views from that wider community about where the UK should be looking to build greater SDA capability. And as I think most of the people at the workshop will know, space domain awareness has been flagged in both the National Space Strategy and the Defence Space Strategy as key strategic priority areas for the UK. So the academic community were invited to participate by reaching out through the GNOSIS network, through SPAN and other networks. Several, and some of you perhaps submitted evidence through the questionnaire that was produced. I should say the CGI were the study leads on this, and so they facilitated the gathering of evidence from people. And then there were a number of workshops, and I was very pleased to see that actually the workshop that was specifically targeted for the academic community had the highest turnout of all of the workshops. So that was great to see the level of interest. So quick trot through, the last draft of the report, which I believe has now been finalized. It does flag up 20 academic organizations across the UK with an interest in this area. It highlights current capabilities and projects, initiatives that are underway, and also mentions some future initiatives. It makes very positive observations about the UK's academic strengths and the UK's international reputation for that. And it concludes, I suppose, brief summary of conclusions is that it makes the case that this is a key strategic capability for the UK, but also makes the observation that the UK is overly reliant on others, particularly for data and also for skills and services. And it makes a case for government to invest more in building national SDA capabilities, and also in forging wider alliances in order to provide further resilience, including a pitch for negotiating re-entry into the EU SST program. Not sure, how government will respond to that, but it then makes a series of recommendations for the government, and I would say most of them are of interest to academia, but some are quite explicitly with reference to the needs of academia. So I will give you the headlines. It recommends that the government should actually produce a detailed SDA strategy and a vision for what the UK wants to build in terms of its national capabilities. that to inform that, it should establish an advisory group around space domain awareness that has representation right across the sectors. One of the observations of the report was that SDA is very much a sort of gray area with dual use considerations, but has been led by defense interests for a very long time. And there is a view that actually that creates obstacles and barriers to progress. And so there should be more opening up of collaboration from defense, civil interests, and commercial interests. And it also makes a case for, increasing international collaboration. This is not something that the UK can develop in splendid isolation. Makes specific recommendations about closer ties with ESA and across the Five Eyes community. It pitches for investment in novel sensing methods and in more sovereign sensing capability in order to have more security of data. I think both Robert Massey and James Osborn were just making the point before the break that the more real data is accessible and available, the better. And so that's been captured, I think, in those recommendations. And then a very strong recommendation for more R&D funding in this space, but also more long-term funding. And it calls for a national research program designed on a sort of hub and spoke model that any interested institution could participate in. It calls specifically for the commissioning of a data accuracy study in order to understand kind of what good enough looks like. We heard Stuart talking about, the need for more granular data, et cetera. And the question is, where do you stop with getting finer and finer sets of data? So there was a view that a study should be commissioned in order to set out the parameters of that. And then a recommendation for what the study calls a collaboration marketplace, which is really in response to an observation that there was a sense that it was difficult for industry to set out its interests and its requirements to researchers, and for researchers also to find industrial partners to collaborate in research projects that academics are interested in pursuing. And so there was a view that a sort of Match.com collaboration marketplace for researchers and industry to come together and find each other more easily would be a useful thing for government to support. And indeed, there's a reflection in there that the GNOSIS network might be a good foundation for building such a thing. So watch that space. And finally, there was a recommendation around continuing to build up the National Space Operations Center, which we know, is already being reinforced, but with an explicit recommendation that needs to be something that supports commercial interests, civil and military users, and that it is, truly a cross-sector operational capability. So that's it. I'm happy to take one or two questions on the study, but as it's a sort of watch this space at the moment, as government always does, they either might publish it in the next month or two, or it could sit on a shelf for a very long time, but it will eventually be published because it's been funded with public funds. So it's going to have to come out at some point. But I thought very useful for this community to know the direction of travel on those recommendations.
Thank you, Katherine. Are there any questions on that?
Well, without further ado, then I think we should hear from the panel members. I'm going to introduce them one at a time, and they'll give brief remarks and talk, and then I'm going to ask people to save their questions to the end so that we can make sure that we definitely have time for everybody to give their talk. The focus here is around collaboration. So let's start with Dr. Emma Kerr. She is the astrodynamics specialist and the technical lead for the Dstl Space Domain Awareness Technology Demonstrator programs. She joined Dstl in January from Demos Space UK, where she was the head of space safety. And her academic careers included working at the Royal Melbourne Institute of Technology in Australia and at the University of Strathclyde in Glasgow. And I think, Bob, you were going to manage Emma's slides, is that right, Emma?
I am. How's that?
You're welcome to take the floor.
I'm displaying okay?
Oh, have we got Emma? Emma, we can't hear you. No, we can't hear you. Okay, Emma's just, we'll do the usual post tea break technical snafus.
Is everything I'm displaying okay though, Katherine?
Yes, we can see the slides. We'll let Emma reconnect, and then if we struggle to hear her again, we will rejuggle the agenda and move her a bit later. Okay. Oh, I think she's back. Emma, are you back with us? You're back with us?
Can you hear me now?
Hello, we can hear you now.
Yay.
And we can see your slides. I don't know if you can see your slides, but I can see your slides.
Yeah, I can. Thank you very much. I do apologize. The Dstl security system is a little overzealous at times. So it does tend to lock us out. Yeah, so Katherine did a nice job of introducing me there. My name is Emma. I have a background in now defense, industry and academia. So I've done a little bit of everything. So I think that gives me a little bit of a unique perspective when it comes to talking to forums like this. I was asked to talk about collaboration with Dstl. I am relatively new to Dstl, so I do have some colleagues on the line with me who might be able to answer your questions a little bit better than me, but I'll do my best. So what I'm going to do today is just talk a bit about what Dstl does and what our interests are, and then how you can actually engage with us. Next slide, please. So I was going to give you kind of an overview of SSA and SDA, but that's kind of been covered, so I'll just skip over this one. Next slide, please. And the next one. Yeah. So in the UK context, there's a couple different things going on that are of interest when we're talking about Dstl. So and SSA as a kind of wider concept. The UK has a continued interest in space. We generate a lot of money out of space, so it is something that we are interested in pursuing as a nation. We've had really great engagement with the international community, particularly with the US, which has meant that we have quite a nice position in the world market. And we have a growing ambition to hold that position and grow it. Within the UK, there have been a couple different programs launched. So the Asteria program covering the NSPOC development. UKSA has its own program developing different technologies. So I was previously involved in their sensor development projects, etc. when I was at Demos. And then we've also got entities like Stratcom who are looking at that population problem that Stuart mentioned earlier. Next slide, please. The Dstl SDA project as a whole has a lot of different things going on. And to be honest, the overarching theme of it really is to answer a lot of those questions that Stuart was asking earlier in his hard problems statement. Our goal really is to provide technical expertise to the wider UK government and government entities like Space Command and UKSA. We develop key technologies. We look at the whole spectrum of TRL from ideation all the way through to demonstrators and ongoing into operations. A lot of the work that I look at is de-risking of technologies, so pushing forward boundaries so that we can actually develop new concepts in SDA through to operation. We also do prototype for downstream solutions as well, so looking at software and kind of like orbit propagation and object characterization, etc. Some of those kind of downstream, less hardware dependent problems. Next slide, please. And as I said, one of our big things is to provide that technical expertise to the Ministry of Defence and the wider government on kind of SDA and developing the UK SDA capability in a few key areas. So some of those are have been mentioned before by Katherine, the sensor solutions, sensor fusion, the algorithm side of things, etc. And one of our jobs is to look at kind of working with industry and academia to support these big goals that the UK has. So when Space Command want to engage with industry, typically we'll work to partner there as well and kind of provide that technical expertise from the government side. And then we also do some kind of horizon scanning stuff as well. So we look at not just what the problems are now, but what the potential future problems are going to be as well, so that we can start to get ahead of that curve. Next slide, please. So some of the key areas that we're interested in terms of SSA or SDA, we are looking at astrodynamics, we're looking at signal processing and signal prediction, we're looking at object characterization, sensing and data processing. We're looking down the road at future sensing capabilities, novel techniques and processing algorithms. And then we also look at things like threat analysis and assessment, modeling and simulation, and also things like space weather as well, that can have an impact, as Stuart mentioned, on several other things. Next slide, please. And then finally, we do some things that are typically not covered by industry. So we look at the protect and defend of UK assets, and we do like space control and threat understanding work that is really necessary for that protect and defend mission. And then we also do some fun things like experimentation, which I'm sure a lot of you on the line have already heard my colleague Simon George talking about the Phantom Echoes project. And if not, I'll give you a little bit of information on that in a second. Next slide, please. So some of the current research that we're doing that I thought might be interesting to the astronomy community, we're looking at developing deep space radar in conjunction with NATO. This is a NATO-led activity exploring the use of long baseline bistatic radar for deep space SSA. So basically what we're looking at doing here is extending the use of radar from GEO that was mentioned, from LEO, like was mentioned earlier, out to using this for GEO object tracking as well. So this would improve our ability to maintain custody of GEO objects and also help us with the characterization work package that we're looking at as well. Next slide, please. So on that object characterization work package, some of the key questions that we're looking at are what is the object that we've got an image of or that we've got a measurement of? Whose is it? What can it do? What's its capability? The reason that we ask these questions, because the traditional SSA view was always just what is it, where is it going, etc. But now with the the increasingly congested and contested environment that we're in, we also have to start thinking about threat. And that capability question is key when we start straying out of SSA into SDA. And we also do some internal activities, so collaborating within Dstl, not just with the SDA team, but also looking at the AI team and the signatures team, etc., and doing some interesting activities with them, where we do kind of short projects to improve our knowledge across these different teams. Next slide, please. One of the other things we're looking at is next gen sensing. So kind of horizon scanning, looking at what are the next technologies that are going to be important for SSA. Our current technologies aren't really keeping up with demand. We've heard earlier that looking at, for example, IR would improve our ability to maintain custody. So it's that kind of the next gen, but then also the gen after next. So what's coming up that could potentially be interesting, and how do we then develop that to a point where we can actually operationalize it. Next slide, please. And then once we've got some fun sensors in place and that we can use, we also need to be able to do the signal processing. So not just the data that we know and things like processing weak signals or noisy data, that's still a challenge, but also looking at the data from those novel sensors and how we're going to process that. And this all feeds back into that loop of things like characterization and orbit propagation. Next slide, please. Then we've also got a project looking at space-based sensing. So thinking about, instead of having ground-based sensors, looking at space-based sensors. So sensors that are already on satellites that we could potentially use in a new way, or launching new missions even with new dedicated sensors on board in order to do some space-based sensors sensing. And space-based sensing comes with its own unique challenges and links back to the signal processing problem. It's a new type of data. We need new ways of processing that. So looking at setting up that the pipeline for this type of data as well. Next slide, please. And then some fun experimentation. So the Phantom Echoes project. This is a collaborative effort where we had sensors all over the world collaborating on tracking the MEV-2 Intelsat 1002 docking mission. And this is a really interesting study. So if you do want to know more about that, I will refer you back to Simon, who can talk to this in more detail. But I know that a lot of you have heard about this before, so I'll just move on. Next slide, please. We engage with NATO. So as I mentioned, we're working on the Deep Space Radar activity. So that's under set 293, and I've put these two in the slides so that you can refer back to these later and find out more about these groups. So 293 is a working group at NATO that you could potentially look at getting involved with. And then upcoming this year, there's going to be a specialist meeting on space sensors and SSA, which should be interesting to everyone here. That's in October this year. So Dstl will be looking to be represented there. Next slide, please. So finally, how do you actually engage with us on all of these interesting topics that I've been talking about? So there's a couple of different ways, and I can speak from experience actually being on the other side of the table on these as well. So Dstl puts out specific ITTs, so invitation to tender, on particular research projects that we're looking at. And these are typically released through the Serapis or ArgCloud frameworks. So make sure that you are signed up to both of those if you're looking at working with us. We also engage through Autumn Equinox, where we contract SWEP. So suitably qualified, experienced personnel. Simon, you can correct me if I got that wrong. But we basically contract in people with specific skills if we're missing those internally. Occasionally, we look to fund a lot of work through the DASA scheme, so through the themed challenges, and also through the open calls. So you can find more information on these on the DASA website. The themed challenges typically have a few headings that you can fit into. The open calls are a lot more open than that. You can actually go in with pretty much any idea that you like, and ask them to fund it, and that'll get passed through to us to evaluate. And then we do things like the experimentations, where we try and do kind of collaborative projects where that it's not typically funded, although I don't want to say it'll never be funded, but these are typically collaborative efforts that look at developing skills and capabilities within Dstl, but also within the organizations that collaborate with us. So I think there's a few on the line that we're involved with Phantom Echoes that can tell you about that experience, where let them kind of test new technologies or using their senses in new ways, etc. So getting involved in those experiments is usually beneficial from both sides. And we also, I should say, part fund GNOSIS, so you can always engage with us at these events, and through the GNOSIS network. We're always happy to hear from you that way. Next slide, please. I think that's all I've got for you today. So yeah, that's a very quick rundown of some of the interesting things going on at the Dstl. If you do have questions about it, then I'll be happy to take them when we get to the question time later. Thank you very much for your time.
Thanks very much. I'm sure that people will have questions after that. So please write them down so you don't forget them, or you can put them in the chat so that people can see them as we go along as well. And then I'll trust Bob to flag them to me. The next speaker is Dins. Many of you probably already know him, but I will give you an introduction anyway for any who don't. He, after 32 years as a commissioned officer in the RAF, Ralph Dinsley, who everybody really knows as Dins, is he is the founder and executive director of Northern Space and Security Limited. He has decades of experience in space surveillance and tracking and in SSA, and as you heard earlier, is involved in academic collaborations already. So Dins, over to you.
Thank you, Catherine. Afternoon, everybody, and thank you for all those that have presented before me. I'm hoping you can all hear me fine. I shall share my screen and hopefully get the PowerPoint presentation up. Brilliant. My presentation has disappeared just at the optimum moment that this occurs. I've had it sitting there waiting as well. So we'll see if PowerPoint comes back to us quite quickly. My apologies
We
about
were
that.
enjoying reading your messaging, though.
Yes, it's very old messaging as well. Okay, it's also disappeared from my recents.
Oh,
I sent
dear.
Bob a copy just
I see
in
it's
case.
the third down on your list there.
Oh, yeah, there we go. Got it. Thank you very much. Although, no, 7 hours ago is not the last time I updated it, because I literally updated it between sending copies to
Did you
Bob
say you
as well.
sent a copy to Bob? Bob,
Yes, I can.
I did send
it.
Can you display that? That'd probably be
sure.
If you could, Bob, thank you very much. Thank you for that.
you.
I don't know. It's
You're rebooting or something, Dins.
Oh, no, there we go. It looks like it's come through now. Yes, it has. There we go. At last. Sorry about that. So it's typical. So it sits there on the screen, and I must have closed out the wrong application at the time. So on with the presentation. Thank you very much for the opportunity to talk about collaboration with small medium enterprises. As you can understand, I'm going to focus very specifically on NORSS's experiences over the past few years. Very quick background on NORSS for those that don't know it. Northern Space and Security Limited is the only UK commercial company dedicated to space situational awareness, the newly named space domain awareness, and we can have long discussions about that, and so I won't get into that today. Space surveillance and tracking, and we are focused on long-term space sustainability and safety in space. I'm actually talking to you from the Kinetic LEO Space Safety Conference in Switzerland at the moment. We pride ourselves on the fact, our USP is very much the fact we have some of the greatest and deepest UK practical experience of SSA and SST between myself and my business partners. So I actually covered 32 years in the Royal Air Force. 16 out of my last 18 were specifically in space surveillance and tracking, space situational awareness, and developing space support for the UK MOD, including leading the operational inputs to both the EU SST program whilst we were in it, and also to the early days of the Combined Space Initiative, which is the Five Eyes military program. Sean Goldsborough, one of my partners, is the lead orbital analyst for the UK Space Agency and has been now for 7 years. Prior to that, he was an analyst at RAF Fylingdales. And Dr. Adam White is the third partner, who has probably about 15 years of experience on academic, commercial, and even government space. And his last role before joining NORSS was to actually work for Dstl, supporting UK Space Agency. We hold a significant share of the UK market on government support for SSA and SDA. We have a team of orbital analysts that work for the Space Agency within the UK SPOC. We provide orbital analysis for the CAA on the regulatory development, and we also actually now have a software program with the Ministry of Defence, and that's utilising all our own people and internally developed unique software and algorithms, rather less innovatively known as NORSS track. We also have our own sensor, which is Loki, and that was created through a grant with from the UK Space Agency, and that's LEO Optical system. It's a camera installation specifically for cost-effective satellite tracking from LEO. Founded only in 2017, we are now expanding up to 24 personnel over the next couple of months and actually beyond that. So our 24th is due to join us in September, but in fact we'll be going out for new rounds of recruitment. We also have the only orbital analyst apprentice that there is in the country, and we'll be advertising and starting the next apprenticeship in September. We are one of only a small number of dedicated space companies based in the Northeast. There are plenty of companies that touch on space, but there's a very few of us that are dedicated to that. And we pride ourselves on our non-traditional space culture, insofar as there may be one middle-aged and a couple of younger-aged leaders in the company, but our team is some very bright, smart engineers, analysts, and apprentices. We also benefited greatly on the software side over the past year, thanks to the government Kickstart scheme. So, in the short life that NORSS has existed, and I must admit, I probably haven't covered every collaboration we've done across academia. One of the most significant projects we started 2.5 years ago was to sponsor a PhD student, thanks to the European Regional Development Fund, in a project that we call the Space Law Games. So it's not just technical, it's technical and policy, and we believe very much that these two things are very interconnected. Technology has a habit of racing ahead of the policy and then gets reined back, or the other side is policy doesn't fully understand the technical and often restricts it quite significantly. So the Space Law Games is very much a capability gap assessment for space traffic management development, and actually looking at can the current technology support the needs of the future regulatory and sustainability requirements of space. We ran a space law games just as the first summer of the pandemic, which was at GEO, and we had hoped to run a LEO one before the end of the project. That's looking highly unlikely now, but it's quite significantly highlighted a number of issues and a number of assumptions. With the University of Strathclyde, we've supported in kind 2 projects to do with both machine learning and space traffic management. And more locally to us in the Northeast, we've also are working very significant projects with Durham University. And as these talk about past and current, there are a number of developing future collaborations that are coming through. So hopefully you get from this the fact that there is a will to participate in collaboration from amongst the SMEs. But my next slide will talk more of the realistic scenarios that we have to face on a daily basis. But we've utilised working closely on small projects with the business school at Durham on MBA market research projects, and more significantly, we're waiting for the potential of an SME market development project on a much larger scale. We have sponsored a postdoc researcher on the data of space requirements. So very much hinged on we've traditionally relied on the US providers with data through spacetrack.org and various other similar ideas, and they're still continuing to develop with things like the Unified Data Library, etc. Well, is that what we really need for the developing SDA market, SSA market, space traffic management market? And so we've had a postdoc researcher on that, and we're putting in some research requests to develop that further. On a smaller scale, we've worked both very closely with the data science faculty and the physics faculties at Durham on a number of data science projects and also optical tracking projects. Quite regularly being advertised at the moment is an MSc sponsorship that we have with the University of South Wales, and that's actually utilising one of our Loki camera systems to be able to do some SST from there, and we're hoping that will develop further into another observatory for us in Wales in the future. And in the past, past 24 months, we've worked on a number of cross-discipline collaborations that are SST grant funded from the Space Agency. We worked with Deorbit and Strathclyde on the Advancing SST grant project 2 years ago, and just recently finished the Phase 0 and A UK Space Agency active debris removal projects. That was led by SSTL, but included a number of collaborations across that project. So for a small company, you can see we actually managed to work alongside a lot of people. But there are a number of what I'd like to call speed bumps as we go along, and SMEs particularly face a lot of these because of the simple size of the companies. Most of our resource has been internally funded and internally developed. We haven't, apart from grant funding, which pays up to about 70% of our costs, we haven't actually gone for any extensive external financing yet. Funding, although it's not at the top of the list, certainly plays a significant part of it, because I think 2 and 5 link very much together. Using the analogy of the tortoise and the hare, of course, research takes time to perform and develop and to conclude, whereas commercial space needs to have that turnover, that rapid turnover, to keep the commercial entity a viable entity, and therefore trying to get that balance between research and pure commercial profit is quite a tough thing. So funding, whether it's through grant funding or through just direct internal funding, is always a significant speed bump for us. And that also links with the size of the company. We were one 5 years ago. And when I say 5 years ago, I incorporated the company on the 8th of May 2017. So we're not actually quite 5 years old yet. And I didn't leave the Royal Air Force until September. So officially, I didn't start the company until much later than that. Most of it was my transition, but then in that time we've gradually grown. 2 of us in 2018, 4 of us by the end of 2019, and then rapidly expanded there. We continue to expand. So the size of the company will always play a significant piece in the ability to be able to support. We get quite a few big requests for research and development support as we go along in collaboration. So we try the best we can, but it's always a problem. And the key bit as well is the experience, because of course the more people we employ, they have, we pride ourselves on the experience of the leadership, and the whole idea of us trying to assimilate that experience across our young team, but that takes time. So again, that links with the size and experience of the company and developing that. And more recently, particularly because a number of these projects are dual use, shall we say? So we're talking about government and military. We have had a few issues with nationality, particularly working on the data science side of things, because for us, unfortunately, there's been a number of requests. We put a couple of projects forward with Durham University, but the majority of those applying for it were of Chinese origin. And because we work with UK military and US military as a business, unfortunately, we can't necessarily sort of share project work with other nations, and that does become a problem. So, as I put there at the bottom, there's a reason we're classified as a small medium enterprise. The problems we find as a company, although we are involved in a lot of things, is the fact that we are small, growing to medium, and trying to balance a commercial need and the R&D need can be difficult at times. And that concludes my input. Thank you very much for your time.
Thanks, Tins. That's great to see actual collaboration in action. I'm sure people will have questions for you afterwards. Unfortunately, Don Pollacco is not going to be able to participate on the panel today, but Paul Chote, who you all met earlier before the break, has kindly agreed to give, I believe, are you giving his remarks or is Bob giving his remarks? I'm just...
So I'll give the talk, but then Bob...
You give the talks, yeah, and then we'll put Bob on the spot to take any questions afterwards. Okay, over to you, Paul.
And any questions specifically on the points from the talk, I'm also happy to take.
Okay.
Right, hopefully that's sharing. Yeah, so obviously I'm not Don. Don unfortunately had to step away for a family emergency at the last minute. So I'm going to do my best to give my view on his slides, which are, yeah, interdisciplinary academic collaboration. So as we all heard from myself and Simon this morning, I'd like to think that we did quite a good job on explaining and showing how the technical STFC skills from astronomy can be applied to push forward SSA research. Yeah, so big kind of differences are that, you know, the targets are moving much faster than astronomy ones, which adds new challenges, but also in some ways makes things easier. Very few things. But then data reduction in general, dealing with cataloging and databases, orbits and orbit propagation, surveys and studies, obviously light curves and high resolution imaging, radar and RF. I'm just repeating our earlier talks at this point, so I think that's been well covered. And yeah, so this is really supporting the big questions that again has been basically covered. You know, all of these topics, which are not just observational. You've also got things related to the orbit propagation, law and licensing we've heard about, and more generally space sustainability. And also, yeah, support for UK assets, which may have different requirements to a general kind of global view of the situation. But a lot of this is inherently interdisciplinary. You know, we don't want to be existing just in an academic bubble, only looking at academic problems. We want to actually have some impact on the real world and try and solve some real world problems. And this, you know, this does extend a lot further than astronomy. A lot of SSA work comes out of engineering and maths departments, which makes things interesting, which I'll come to. You know, a lot of this work is, well, certainly my experience, I'm not sure if this is where Don wants to go with this, but my experience is that, you know, these different groups have got very different terminologies for the same things. And sometimes you can spend 2 weeks trying to just work out that you're talking about the same thing. And so it is quite difficult to break the ice with people from these other areas, and that does make collaborating a bit difficult. One thing that I should mention, because it's on the slide, is that we're fortunate to have significant facilities in one of the world-leading astronomical sites, and that puts us at Warwick's in a very good place for collaborating with both industry, testing cameras such as with Andor, and also with Dstl, and collaborating on these big observational campaigns such as the Phantom Echoes project, which I'm sure anyone who's been to the last few GNOSIS talks is probably sick of me presenting the same slides on. So kind of in the theme of interdisciplinary collaborations at Warwick, we created a Centre for Space Domain Awareness last year, which is initially bringing together our SDA research with also the plasma physicists who have been at Warwick for quite a while. And they're interested in a lot of the space weather side of things. And also bringing in astrodynamicists from the maths department. And we now have just brought in a new postdoc in astro on this as well. But again, this is, early stages of collaboration. And as part of this, we've also recently spun out, incorporated a new company that you'll hopefully hear more from in the hopefully not too distant future. Okay, so kind of one of Don's bugbears on this, and certainly a challenge that we've faced, is finding funding for this research. With astronomy, we're used to being able to deal with, have the CG providing a baseline of support, and then other schemes from a research council. But the kind of SDA area does fall between the cracks, and that makes things difficult. So we've relied a lot on local funding, but we have had quite a lot of success through STFC, obviously getting GNOSIS funded, and then being able to have GNOSIS give out grants, to which I myself have taken advantage of. There's also impact funding from STFC and EPSRC, and specifically the UKRI knowledge exchange schemes, which is another area that we've been quite successful at, with an IPS fellowship, and also a class grant for our LEO observation ideas. Don suspects and has been pushing lately that it might be possible to get grants through EPSRC early career, but that's not something I know a lot about, so unfortunately I can't talk about that. And then also these UKSA irregular calls, which is something we've done a bit with. But no CG support on our part so far, but we have actually been able to get some PAT time, which is the STFC telescope allocation. So we got time on the Isaac Newton telescope to do the geo survey that I talked about this morning, and also via class we have got a project that we're running now using the mop-top polarimeter on the Liverpool telescope, which we're then combining with optical observations that we're doing simultaneously from our facilities that are just a few hundred meters away from the Liverpool telescope. And that's going to be quite exciting, we expect. Got the first data for that last night, so we'll see how that goes. But there are some non-traditional sources of funding that are useful, and which we, again, have had a bit of success on, and that's these DASA calls. There have been 2 or 3 in the last few years that have been specifically SDA related. But from an academic perspective, these have been a bit challenging, mainly because you put in the proposal, you hear the results, and the result is, okay, you've got them, we need you to start in 2 weeks' time. And that is quite difficult with the university bureaucracy and being able to recruit people, because the university wants you to have funding for people before you get them, and it's not really possible to recruit people on such a short window. And then, yeah, within the UK, the EORD scheme has been quite useful. We have a PhD studentship funded through them, and they seem quite keen to be open for other people's research and funding new things. I suspect Don would have had more to say on the slide, but I'm going to have to leave it at that, I think. Yeah, so I'll leave it there and apologise on behalf of Don.
Thanks, Paul. I think if there's anything on that slide that that Bob can answer later, we will certainly be happy to pass any questions to Don for just a direct response to anybody who's attending today. Thanks very much for that. I'm just going to rejig the agenda a little bit and ask Massimiliano to take the next slot, with thanks to James for his patience. So quick introduction, many of you will know him already, but Dr. Massimiliano Vasile, he's the Professor of Space and Systems Engineering at the University of Strathclyde and the Director of the Aerospace Centre of Excellence. He coordinated the EU-funded Stardust network on asteroid and space debris from 2013 to 2017, and is now coordinating the follow-up project, which is called Stardust Reloaded network, and that's focused on space environment management and asteroid exploration. And I'm sure his talk is going to explain what that network is up to. So over to you.
Thank you, Katherine, and good afternoon, everyone, and thank you for inviting me to give this talk. So what I'm going to explain is what Stardust is and how it started, why it started, and what is now Stardust Reloaded. So the first Stardust was a Marie Curie network, ITN, funded by the Framework 7. We got the grant in 2012, and we started officially in 2013. So we got 4.1 million euros to set up a network that was covering both space debris and asteroids. And I will explain why I had the idea of creating a network that was covering both topics at the same time. So the network was fairly successful. It was listed as one of the success stories of FP7. And it started with a fairly small number of institutions in Europe. We had 10 partners plus 2 or 3 collaborators. But then during the development of the network, it grew a lot. I mean, we had a lot of people who wanted to join in, so they were associated to the network as partners. And by the end of the funding period, we had about 20 partners involved in the network. And so we decided to submit another proposal, this time to the H2020 framework program. And luckily we were awarded another grant, this time for 3.9 million. The reason why it was less money is that there were less UK institutions involved in this second grant. And Stardust Reloaded started in 2018 and started already with a lot of partners, many more than before. So we had about 20 institutions already in Europe, plus this time we had from the start 4 overseas affiliated partners. And this is the number of institutions that we have in Europe. So we have a mix of academic institutions, and we have space agencies. in the first Stardust, we had only European Space Agency as one of the partners, while this time, because there was an interest also from DLR and CNES, we started already with other 2 agencies involved. And we have also companies. So some companies like Deimos are receiving funding and are developing specific parts of their research program. Other companies like Airbus are providing support to the development of some of the activities. Exactly like ESA and CNES, they also provide access to expert personnel and data. We have, for example, people seconded at ESA and seconded at the French Space Agency, and they work with them on the development of some of the algorithms that they need for example, SST. The network has a variety of expertise. For example, we have in Germany the FKI that is very much focused on robotics for active debris removal. So they are looking at that kind of area, including on-orbit servicing. We have other institutions like the Observatory here in Belgrade and the university, or the University of Pisa, that have been involved for now more than 2 decades in asteroid monitoring and impact monitoring. So they provide a lot of the expertise in that area. As I said, we in Stardust Reloaded, we started already with collaborations outside Europe. So we have 3 institutions in the US. In fact, we after the start of the project, we included also MIT. So we have Stanford, Arizona, and Texas. You probably know who is at Texas at Austin. Morima is working there. And then during the development of Stardust Reloaded, we also included a group at MIT. And I didn't put it on the map, but we also have a collaboration with the team in JAXA who work on Hayabusa 2. So for the part of the network that is dealing with asteroids, we also have that collaboration. So how it started and why it started, the reason is that at that time I was dealing mainly with asteroids and planetary defense. We're talking about 2010, 2011. And I realized that a lot of my interactions were not just with people doing asteroids, but with people doing space debris as well. And in fact, if you look at the 2 communities, the interesting side of the 2 communities is that they do pretty much the same kind of things with pretty much the same kind of technology. So they acquire measurement or observations, optical or non-optical, and they have to do orbit determination and predict possible impacts or collisions. And then that's where the 2 communities differentiate a little bit. In the case of debris, the technologies that are used to remove debris are not exactly the same that you use for deflect asteroids, although some are also in common. For example, you can use lasers in both cases. And the ultimate goal of some of these technologies is to get rid of the threat connected, for example, to an impact with an asteroid or with a piece of debris. So I put together basically the 2 communities, all the people that I knew in Europe that were doing one or the other. And in fact, the interesting thing is that they were all interested in working on both topics. And so it was easy to put together a program of research that was cross-fertilizing. So that was taking techniques from one area and supporting the other and vice versa. So in Stardust, we looked at many different things. We looked at precursor missions for monitoring or reconnaissance mission for asteroids. We looked at impact probability, deflection techniques for asteroids. But we look also at the stability of the environment around the Earth. In particular, there was a lot of work done on the stability of the MEO region and the stability of the geosatellites. One element that was important for the first Stardust was the ability to remove debris. So we developed technologies for active debris removal, as well as the study of the dynamic evolution of debris in orbit. And for the first time, we introduced this idea of having an open source code that was doing re-entry analysis very fast, so that would allow fast deorbiting and re-entry analysis under uncertainty. So it could provide also this added dimension of the uncertainty in the re-entry and the probability of hitting the ground. So when we then had to propose Stardust Reloaded, we decided to take a slightly different direction. There was already at that time the emergence of the new space movement, Space 4.0, mega constellations going up. And so space traffic management was becoming really a critical aspect for the future of the sustainability of the space environment. So we focused the research program on technologies for space traffic management in view of making space sustainable, and also to study the resilience of the space environment to the increase in traffic and inclusion of these mega constellations. So the element of risk, uncertainty quantification, and prediction of impact is one of the key elements. And we decided to add that to another emerging technology that is the use of artificial intelligence to improve space traffic management. And since the network is covering both sides, one of the things that we decided to do is to apply the idea of criticality indexes to asteroids. The criticality indexes is something that was created for space debris. So we decided to import this notion also in the field of asteroids, and to study very small objects that are coming from, for example, from the asteroid belt and can regularly intersect the orbit of the Earth. So in summary, what we are doing is to work on artificial intelligence and uncertainty quantification to improve our understanding of the risk connected to objects in space and all possible consequences of increasing the traffic on the stability of the space environment, and the increase, for example, of conjunction event and collisions. We're working also on design for demise and the problem of predicting correctly the re-entry and fragmentation of objects from orbit. And in parallel, we have a series of work packages that instead are focused on the exploration of minor bodies and the understanding of their composition in view of also possible planetary defense actions. There is a conference this year that maybe all of you might be interested. Is in November, from the 7th of November, is ESTEC in collaboration with the European Space Agency. So if you visit our website, we are going to put more information. We have two tracks. One is focused on space environment management and sustainability, and the other one on asteroid exploration and exploitation. So please visit the website, because we are opening the registrations probably in a month's time. Since the other people included a slide on funding, so I decided to put one as well, looking at the future. So of course, being the coordinator of a European network that has been successful, I wish I could access EU funding that is growing in the area of SST, in fact. But as you know, we have serious restrictions on that. So luckily, ESA is always available. Someone said that ESA has sporadic calls, but it's not actually true. I mean, ESA has regular ITTs. There have been least 5 or 6 ITTs only in the last year. But ESA has also programs that allows bottom-up proposals, so unsolicited proposals from TRL 0. For example, here at Strathclyde, in the last 3 years, we secured 11 grants just on SST and SSA. So not a lot of money, but a continuous flow of money, because there is behind that a long-term program. So the Space Safety Program, Clean Space are there to support these activities. I wish that there was a program also in the UK to have a continuous flow of calls from the UK Space Agency. That would be really something needed in this area. We also managed to secure funding from the Dstl and DASA. That is a bit more regular, and I think it's a good indication that there is a strong interest from the Dstl. We're working currently, for example, on a project on intercontinental radars that is quite interesting. And that's me.
Thanks very much. I'm sure that people will, if you can stay long enough for some questions, we'll want to ask a bit more about how more organizations can get involved. But first, let's give James a chance to speak. I'll introduce him. He's James Endicott. He works for the Open University. Hi, James. And for the past 3 years, he's helped to grow the space academic network and provide coordinated inputs from the space research community into government. His prior experience was in industry as well, working closely with academia. So James has the benefit, as Emma does, of academia and industry and government relations in this case. He is a PhD trained physicist with background in semiconductors and image sensors. So over to you, James.
Thank you, Katherine. So hopefully I recognize a few names in the meeting, and a few people will be familiar with what we do at SPAN, but the aim of my presentation is just to give a quick overview of what the Space Academic Network is and where we are at the moment. And then I've summarized a bit of a view of the funding landscape. So I think this is something most of you are probably familiar with, but it's always, I think, useful to look at the big picture numbers. So that's what I put together on the slides, and it sort of reinforces some of the points from the previous speakers. So we'll just cover that. And then the final thing I'm going to talk about is what we've been sort of proposing as initiatives or ideas for new funding to help grow space research. Okay, so the Space Academic Network is a recognized voice for space research in the UK, and we represent space research in 4 broad areas, so science and exploration, Earth observation, technology and engineering, and data and analysis. And we've structured the network with a board that meets 3 times a year, and then underneath that board, each of these sort of topic or domain areas are discussed in working groups. But as SPAN has grown over the last few years, it's got the picture's got a little bit broader and a little bit more complicated. So we also have a strong link with the UK Space Life and Biomedical Sciences Association, for instance, and we've also formed a position navigation and timing focus group that sort of sits under the umbrella of our engineering and technology working group. And we're open to sort of new working groups as required. So for example, you know, if the community wants to self-organize under a specific working group, then that can be considered. I should point out that membership or participation in SPAN is open to any career researcher. So we welcome anyone who's on a research career path. And then we operate a kind of on the board. So universities that co-fund SPAN have a place at the board, but otherwise we're supported by a modest grant from the Space Agency. We're also transitioning the leadership of SPAN from the Open University to the University of Leicester this year as well. In terms of our membership, so we represent 43 universities with over 200 active members who are scientists or engineers, and there are also a number of national centres and represented within SPAN as well. So we have quite a broad reach. In terms of who we talk to externally, so we talk to BEIS and the Space Agency in UKRI. So that's BEIS is the Department for Business, Energy and Industrial Strategy. We've been actively involved in the Spacecraft Partnership. So that's a body that coordinates government, industry and academia. And in the last 6 months, there's been a national space partnership that was piloted, that was intended to replace the Spacecraft Partnership. So that's a bit of a evolving activity in the UK space sector. And then we also engage directly with UK Space, the trade body. We have links to the Royal Societies and other bodies such as Dstl, who are represented in this meeting. So on to funding. So funding routes, I guess the first thing I think of is UKSA and ESA. And one way of looking at ESA is really it's a mechanism for UK investment. So, you know, this figure is taken from the last published annual report from the Space Agency, and you can see that the majority of the money that the Space Agency receives from BEIS, its parent organisation, goes into ESA, and with the intention that that is returned back into the UK, either industry or academia. And the positive thing is that it's been following an upward trajectory. Currently, you know, the Space Agency are developing the business case for the next ESA ministerial, and we hope that, you know, there's further investment in ESA. At least that's the consensus view from SPAN. But outside of ESA money, we have UK's national programs. So that's, I don't know if you can see clearly, but it's the sort of what colour would you call that? Almost burgundy line on this plot. So the national programs are quite small, and in the year 2020-21, it was of the order of 50 million, and half of that went into grants to academia. So relatively speaking, you know, academia does well out of a small pot. But unfortunately, it gets salami sliced down, and you have opportunities such as the National Space Technology Programme, but it only amounts to a budget of, say, single-digit £1 million per year. So these are not large sums of money, unfortunately. What has been initiated in the last couple of years is the National Space Innovation Programme, but it's been restricted to Earth observation and communications, but there's potential for that to be a growth opportunity in terms of new funding that might support the interests of people in this meeting. So in terms of the ESA investment and how it was spent, 4.5% of the UK's money into ESA was on situational awareness. So that's a modest to sizable pot of money that was spent on space situational awareness. But again, these figures are taken from the agency's annual report, and you know, the kind of priorities or insights into their priorities can be seen that, you know, they talked about new developments that they highlighted were on, you know, Lunar Gateway, sample return from Mars, new satellites for climate change, warning systems for solar storms, and so on. So I think, you know, there's a role to sort of increase the, I guess, you know, prioritization of space situational awareness to make sure that it's forefront in the agency's mind and reflected back in their publications. I think that would help increase funding for your areas of interest. Another funding stream, of course, is UKRI. So again, from the annual report, this the breakdown of the funding of UKRI from 2020-21. You can see across the different research councils, they had about 4.9 billion in R&D funding, where in SDFC it was 477 million. But unfortunately, we know that budgets in SDFC for astronomy have been pretty much flat for a long time. But the latest feedback I've had from Colin Vincent in SDFC is that the status at the moment is their advisory panels are working on updated roadmaps, and we see that will be completed by the summer and will guide their strategy for space. They're planning new grants schemes that will offer more flexibility, and apparently there's going to be a community meeting this month to discuss it, with the rollout expected next year, and they're hopeful of some uplift in the grants budgets next year to reflect the underinvestment. Then the sort of third thing I wanted to talk about was defence funding. So in terms of new sizable funding pots, I guess this is really the one we can look to in recent years. So the defence budget was announced in 2021 with 6.6 billion funding for R&D over a 4 to 5 year period. And as we've heard from Dstl and from others mentioning Dstl, their priorities are aligned with space situational awareness, the space environment, intelligence, space control and resilience, military satellite communications, satellite launch, space architecture and advice, and space position navigation and timing. They're also interested in what I see as complementary areas. So, artificial intelligence, autonomy and robotics is an active area for space research. Space has a role in cyber resilience. Underwater might seem like an outlier, but there's some parallels between underwater environments and space in terms of resilience, but also autonomous systems. And then they're interested in energetics and weapons. So in terms of what we've been doing in SPAN to try and change the scenario or funding world that we're in, we've been promoting a couple of initiatives over the last few years. So we have been talking about a small satellite science program where it would give the UK an opportunity to have a domestic or national science program, which would be open to all activities of science from space, so that'd be looking down or looking out. And this is with a view to maintaining and building capabilities in the UK, an outlet for sort of innovative mission ideas, precursors that would lead on to bigger missions, either with international partners or through the space agency. We've also been talking about technology hubs, and we see this as a vehicle for collaborative research between academia and industry, and also a channel for commercializing research. We've been talking about science bilaterals that will help us to do things in addition to our main activities through ESA. We've been talking about SPAN fellows to help grow and support our activity in the network. And finally, on sort of advanced skills training, we've been pushing the case for space technology doctoral training centres. And in the last year or so, we've been putting forward these ideas in a number of fora. So BAYES developed their strategy in the last year, and we made inputs into that strategy, echoing our ideas for these initiatives. There was also a House of Commons Science and Technology Committee call for evidence. Again, we made inputs into that. And finally, in the autumn, there was also inputs into the comprehensive spending review. And again, we put papers into these. So we remain hopeful that in the coming years that some of these ideas are funded and supported to support the research community in the UK. And I raced through that to try and win back some time before the panel session. So that's what I wanted to say on an update of what SPAN is and what we've been trying to do, with a sandwich of an overview of some of the funding landscape.
Thanks very much, James. And you've been very effective at winning us back the time. So I appreciate that. I think I will, just for your sins, then start with you as a question for the panel. There's a question from James Osborn in the chat, asking, how does SSA fit into SPAN? So have you had an opportunity to think about how this community of astronomy, can fit with the SPAN proposals in order to get more involved in SSA?
Sure. Well, I guess in the first instance, a lot of astronomers are telescope agnostic. They use data from ground-based telescopes, or if their telescopes happen to be satellites, they'll also use the data from there. So I think there's this overlap and almost no boundary if you're an astronomer. You're looking at space, and your instruments are either ground-based or in space. So I think there's a role for SSA within SPAN in that we have many astronomers participating in SPAN. Whether or how it needs a separate sort of forum for discussion, certainly open to that, but your network is one forum for it, and rather than duplicating, creating links or improving the links between SPAN and GNOSIS is probably a more sensible way to go.
I agree. I think that's a sensible thing. We should be carrying on working on that. There's a question from Mike Hapgood, sort of to everyone on the panel, but so I'm going to open it up. But I suspect the answer is that nobody on the panel will have a direct answer to this. The question is, are there any plans to develop a more nuanced economic impact analysis for space domain awareness? I open it up to the panel, but my own response, sitting in the seat that I sit in, is that I think that's a piece of work that really needs to be done, and somebody should be bringing forward an economic impact proposal, study proposal, and should be pitching that into the space agency. But is anyone on the panel aware of such a thing? Max?
No, but I would say that I think that there is no complete or updated economic impact study of not doing space traffic management. And so even before quantifying the cost of current space traffic management practice, probably we need also to understand the impact of not doing it at all, or not doing it as it should be done.
Yeah, I agree. I think that SDA report, the SDA capabilities report, did try and take a look at the risk, the value of the risk. What was at risk if actually we didn't build better capabilities? But that was sort of not the most in-depth economic assessment. Dins, you got your hand up to say something.
I think this actually is a good question insofar as it generates a need for a number of different economic studies, whether both the impact of SDM, the impact if we have the catastrophic space event, and maybe it's something for our Black Swan event in October for GNOSIS. One thing I've discussed and still waiting to hear back from a salvage expert angle is actually the cost of what is on, or not necessarily the cost of what's on orbit, but actually the economic value of reclaiming what's on orbit or recycling it as well. So I think there's a number of economic impact studies that should be carried out.
And certainly I know of researchers who are very interested in addressing the circular economy in space, which is a related topic there. But I suppose slightly bringing it back to astronomy, I did say, Max, that I would ask, how can more UK organizations get involved in Stardust?
That's fairly easy. I mean, we recently included Imperial because we have a collaboration with a group at Imperial. So now Imperial is a partner. I mean, the unfortunate thing is that we cannot share the budget that we have because the budget is allocated only to beneficiaries, and those cannot change. But we can use part of the budget to do other things. So develop pieces of research, support collaborations, and so it's just a matter of sending us a request, and then it's very easy.
Okay. I suppose I will just point out that in the defense space strategy, there was specific mention of increased budget for building SDA capability, 85 million over the next 10 years to be spent on SDA. And while I'm sure some of that is operational budget, you know, looking at building out the National Space Operations Center capability, I presume that there will also be research budget somewhere within that envelope. I don't know, Emma, if you have, or any of your colleagues have any intel on that, or anything that you could share, at least on the process around what might happen with that 85 million pounds.
Sure. So I can't speak for the whole budget. I can speak for what I get to see of that whole budget, which by the time it gets filtered down to me, it's a lot smaller. But yeah, we're definitely seeing an increase in our budget this year, and the money that the STL has to play with. So I would expect that we'll be putting out a lot more research to industry and academia. So watch this space. We're just developing those statement work just now.
Okay, that's good to hear. And a sort of related question, I was interested, Dins, I'm going to put this to both you and Emma while Emma has the floor. I was interested to see this announcement on Monday. I'll put a link to an article in the chat of SpaceWorks, the technology arm of the US Space Force, just placed, I guess they're very expensive sort of proof of concept type studies with budgets that obviously the UK, you know, couldn't even dream about, but had just placed, awarded 125 bidders study money so that they could then, you know, come back with interesting solutions in the general realm of space security and sustainability. Now, some of that will be SSA related. I suspect quite a lot of it might be debris removal related. But what was interesting there was a reflection in that article that I read saying that, and they thought that insisting on SME and academic collaboration for the bids for that would really curtail the number of parties coming forward with an interest, and the fact that they had considerably more than 125, so that they whittled it down to a short list of 125, meant that actually that didn't pose a barrier. So I'd be really interested for you, Dens and Emma, to just talk a bit about how you foster SME academic collaboration. You know, maybe some people who aren't on the panel would like to chip in with their thoughts on that as well.
Emma, do you want to speak first? Are you happy for me to talk?
On you go.
It's an interesting point, really, because there's I wouldn't say there's lots of barriers for fostering that sort of working together. Just as an SME, the barrier is just the size of the company. I mean, there's certainly gaining company reputation is very, very important. Significance of the reputation, yeah, and getting out and visibility across the research sector rather than specifically the commercial sector is sort of mainstay to do that. But I've rarely had to reach into academia about working on projects. It's always mostly been nearly virtually 100% been the other way around, where academia has come to us and said, would you be interested in working on these projects? Because of course we add an experience angle in the field, which we're fortunate enough to be a company that holds a significant amount of that experience, and there's so few companies dedicated to what we do. I'd be interested more in an SME that was in a market full of other similar companies and how that would work. But we've worked with, when Emma was at Demos, we've worked with Demos before and generated that work with other communities. And for us as a company, I think some of it has been also based on the fact that we supported UK for UKRI, but SDFC in the USST program as a fledgling company, and that helped to get our visibility out there as well.
And Emma, what do you think about that sort of, enforced collaboration between SMEs and academics to drive innovative thinking?
So I don't know whether to answer this from my current perspective or my previous perspective.
We have the advantage of you having worn many hats. Let's hear your personal perspective. That's fine.
Yeah, I mean, so when I worked at Demos, that was an interesting challenge for us, making sure that we had enough academics on board to do certain projects. I mean, while I was working there, we actually put in a proposal for GNOSIS funding that ended up getting rejected because of the lack of academic support, which is challenging for small companies. But I do see the reason behind it, because I think that there is a huge benefit to be had in having that academic SME partnership, because I think each of them has something really unique to bring to the table. So I see the reasoning, and from my current perspective, I think that that's really positive for how we do it. I think, I mean, the majority of the research that we're looking to conduct is fairly low TRL, so that tends to encourage that type of partnership anyway, because typically academics are looking at the lower TRL compared to industry. So it does tend to generate that just naturally. So we're not really looking at forcing it, but I can see the reasoning behind it, for sure.
So Ian Bryson has put a question in about match funding and whether that's that's an issue, because so much of the funding in the UK requires the SME providing match funding. I don't want to go too far down that rabbit hole, but I just found it interesting that it was evident that there is such an appetite in the US for SME academic collaboration around this sustainability topic. Now, obviously, the SpaceWorks has very deep pockets, and I'm sure Dstl would love to have a budget like that. But within that, Max is going to need to go, which is thank you for your time, Max. And yeah, everybody get in touch with him if you want to get involved with what he's doing there with Stardust. And James, I'll come back to you about the ESA funding, because what Emma's saying about low TRL, that does seem an area where industrial and academic collaboration, can be successful. And I'd just be interested to hear your advice, for people who might be interested in getting more involved in the space safety program. I think obviously knowing how that process works, the space agency, UKSA, has got to be supportive of people bidding into ESA for ESA funding, because at the end of the day, on the geo return, that money actually comes out of UK taxpayers' pockets in the first place. So do you have advice for how astronomers could, get more involved in the ESA space safety program topics?
Well, thinking about, the ESA sort of ITT process and so on, you have to be actively monitoring it and looking out for, filtering for the ones you want amongst the plethora of ones you don't want. So that's a challenge that you almost need like a bid manager to be doing that for you. So I don't know whether, there's kind of some central capability in any of the universities that can do that. Either that, or you need warm relationships with an industrial partner, either small or large, where you almost have like a memorandum of understanding in place. You know, if something like this comes up, you know, we'll jump on that opportunity to get together, because yeah, so one piece of advice or recommendation is kind of having those one-pager outline sort of projects of things we would like to do should the opportunity arise. But something I'd really like to comment on, I guess, is, you know, Katherine, you mentioned a hub and spoke model, and I've mentioned technology hubs, and I think that you know, space situational awareness is kind of quite ripe for an academic industrial partnership, you know, multi-party sort of hub, if you like, or collaboration. And I know that in a few years gone by, there are ideas of putting forward things like this under, you know, Strength in Places funds, but, you know, those are no longer available. And for, well, any of these sort of big consortia proposals need quite a bit of effort put into them to bring them together. But, you know, I think you could probably do an unsolicited proposal, but you'd need to pitch it into sort of possibly UKRI, because it could be cross-council, but there is a directive for sort of cross-council projects, and we proposed our sort of short list of space technology hubs to them, and there was a sort of warm reaction, but we didn't sort of pursue that as hard as perhaps we might have done. But I think, you know, for this community, that's something that could be considered if you wanted to kind of construct an outline proposal of what you'd like to do. It also makes me think of it's sort of something that would have fallen under the Space Growth Partnership or the state national space partnership, where, you know, you've got these topics where it's not the single domain of academia or industry or government, and government in its different guises, you know, and it's something that really has to be delivered by a partnership. So I'm not quite sure where those kind of partnerships are going to be in the next 6 months, but, you know, that's another sort of thought where you could really look at this as more than just academia and industry, but it has that government role in it as well.
Absolutely, and I do think that the Space Growth Partnership is now transitioning, or at least that's the intention, to the National Space Partnership. And the intent there is that it should be looking at future challenges. It should be drawing together, you know, combined proposals or cross-cutting proposals between industry and academia. I think it has some way to go, but, you know, finding its feet before it's able to really be the conduit for that. But here's hoping that it would provide a forum, at least, for those kind of proposals to come together. I think, you know, we will continue out of GNOSIS to raise those questions, to speak across research councils, etc., and to try and draw groups together, interested parties together. And I know there are a number of new space groups popping up around the country, which is great, and making sure that actually they are involving their astronomy communities, you know, at those universities, and that the astronomers know about the opportunities to get involved in SSA. I think that's one of the critical things that we're trying to achieve. I'm going to just slightly expand that, see if anyone else on the panel has anything that they'd like to say about that. And if anybody who's attending has any specific questions for panel members, otherwise I will ask another question. Did any of the other panel members want to reflect on what James just said?
I would second the memorandum of understanding point, James. That's a great idea. When I was working at Demos, it was really challenging to find the right partners. So if you know what other companies are interested in working on with you, then it makes it so much easier to put those consortiums together. Because a lot of the time, particularly for ESA ITTs, they are hefty documents to put together. So you need quite a lot of time to prepare. So the less time that you spend putting together your consortium, the more time that you have to work on your bid. So yeah, I think that's a really great idea.
I think just to say, this idea in that SDA study report around collaboration marketplace is absolutely something that GNOSIS would like to explore going forward. But the question I'm going to pose is around the cultural challenges. And, you know, when you say have MOUs in place, from my prior experience, I often advise researchers and companies to have what I call oven-ready proposals sitting on the shelf, you know, that they would dearly love to deliver and know how they would deliver it should the funding become available. And that sort of MOU where you've already agreed what work you would do together if you could secure the funding, I think is a really good idea. And it does speed up the process then of being able to bid. So my question is about this barrier, how you make sure that academics aren't, you know, holding all of their proprietary ideas so close to the chest that industry doesn't know, you know, who they could work with, and likewise that industry, you know, who are reluctant to put their priority areas for R&D out into the public domain because they're concerned about their commercial position. How do you overcome those barriers? Dins?
I don't think I was going to be able to give you any answers to that, but I was just going to reiterate the significance of the, I suppose, of both the IP issue and the commercialization issue. It sort of fits hand in glove with the hair and the tortoise piece as well, the fact that research and development will take time. So finding, one thing that we're researching with our friends at Durham is how we can develop research projects that provide almost like commercial milestones en route, and so therefore you get some commercialization out of it as it develops, as well as continuing that long-term R&D project. The IP piece, I think, is also one that's always going to be problematic, but going back to the MOUs and having that that understanding and that close working relationship is the important piece.
Yeah, and I suppose also, as has already been raised about recruitment timescales, I think raised by Paul through Don's slides, that, you know, maybe having those MOUs in place, you know, gives a bit more of a planning time horizon. But is that still an issue, the way that funding can be made available for these things? Bob, Paul, I welcome your.
Yeah, I think it is, in that typically actually the sort of the astronomy groups or the engineering groups actually won't have staff around. You can just immediately move on to a new project, in that everyone is on a project which will be a year ahead or whatever, which means I think it is an issue, and I think that the strength of interaction with academia is if you can exploit skills and expertise in the longer run, which means you need a sustained interaction, which means that there's enough of an understanding of needs and interests that you can build up a longer term collaboration. I always think actually that studentships are a means of sustaining interactions, and I'd be interested and hear if others on the panel would echo that, in that often it isn't as much actually what the student achieves as having the student as a means of aiding interaction over 3 years, if it's a doctorate, say.
Interesting. Paul, you might have a view on that.
Yeah, I kind of echo Bob in that, but I'd also add that it would make certainly our lives a lot easier if the funding providers could provide more longer horizon opportunities. Because at the moment, almost everything is these very quick, very reactive, you get the funding, you start in a couple of weeks, you're finished in 6 months. And that if there were some of these more, longer horizon, more collaborative things, it would make it easier.
Well, hopefully both the defense budget and UKRI budget having been settled over, a longer time horizon might allow for less last minute itis in the way calls come out in future. I'm going to again invite anybody who's attending the workshop to put any questions in for any member of the panel. But I guess in the meantime, I'm going to just put a general question out for all of you about, how can astronomers who are new to SSA, and there have been a few side chats over the course of the workshop about people asking, I have an asset, how can that be leveraged? How can astronomers who are new to SSA get involved in this area of research? Resounding silence.
I'll say something then. I'd recommend firstly having a look at the calls that are open and thinking about how they might contribute, but also actually just going to companies that maybe have similar assets. So putting my Demos hat back on, Demos have their own observatory and they do their own optical measurements. But there are certain challenges that you can only do if you have 2 sites, for example. So in that case, Demos would probably be willing to partner with them to do the knowledge sharing that's required to then get that extra data from a new site. So that can be a really easy way to build that knowledge if you don't have it already. Mm-hmm. But then, building the collaborations, attending conferences that SSA is presented at is a really great way of engaging. So attending AMOS or IAC or the GNOSIS events is a really great way of engaging and finding partners that might be interested in working with you.
Thanks, Emma. And I'll also just give a sales pitch for GNOSIS because we do still have proof of concept funding available. So if there are researchers who just want to test an idea, go find a collaboration partner, who would be happy for, the bulk of that cost to be covered by GNOSIS funding and put your proposals in. The clock is ticking though, so because we've been running for some time now, so our current pot of funding, we do need to have those studies and things delivered by the end of the financial year. So, we've got a good run at it. If it is something you just want to develop an idea and test working with a new partner, by all means, bring proposals to us. Anybody else have any other advice for astronomers who want to get involved? I'm going to also just slightly expand that because this topic area, this sustainability area and SSA is really going up the agenda. And as I said, at the beginning of my little report back on the UKSA SDA study, space domain awareness, which goes beyond SSA, but includes an awful lot of SSA techniques within it, is a priority in the national space strategy and the defense space strategy. So there's going to be quite a lot of activity in this area. And as we've seen from that article that I saw on Monday, there's going to be quite a lot of activity in other countries as well. So how do we get new astronomers, i.e. younger generation, people just starting out, on their astronomy careers, how do we get them involved in this topic area? How do we get them interested in it? Open that up to the whole panel.
Well, I'll jump in there. I suppose noting that Robert Massey's attending, he might comment on this as well. But maybe in the next National Astronomy meeting, it would be an opportunity to promote the activity. So you could ask the organisers of that meeting whether you can have a either some sessions or something appropriate on SSA.
Indeed, actually, we are organising holding one, in fact, already. Yes, that's a good idea, and it's in hand and will be happening at NAM in July. So yes.
Yeah, I bet I'm chairing something at NAM, so I should say we're definitely going to be making noise about it at NAM. Yeah. Any other remarks? You've been invited from the floor, Paul.
Yeah, so kind of following up on that, I would say a challenge, particularly in getting PhD students, is we need to be able to show that SDA is sexier than, say, exoplanets. We need to get enthusiastic people who actually want to do this. And that is, I think, something that we've managed to improve over the last few years with GNOSIS and stuff, and also the increased media attention. But I think there is still a long way to go. And things like sessions at NAM, I think, are very helpful towards that.
Good. I obviously think it's sexy, but maybe we need more spokespeople out there, giving the sales pitch. Robert Massey.
Yeah, I mean, look, I absolutely agree. We could have more sessions. And the other thing is, if you're interested, particularly in early career scientists, we have a really good early career network, and why not? If there's a company that wants to come along, or a group of companies that wants to come along and pitch it to people who are currently doing doctorates, for example, I'm sure they'd be up for it. They're really very much about looking for different career opportunities in and outside of industry and academia and crossover and so on.
Thanks. And Emma?
Yeah, so Simon's just messaging me. He's suggesting apprenticeships and public outreach. So capturing them even younger. It's like, don't wait until they're in their PhD already and already focused on exoplanets or whatever they think is sexy. Get them interested at a high school level, even funding schools to do like basic telescope satellite watching events and ISS hunting, that sort of thing. Get them interested really early on.
Yeah, I agree. You might know in my spare time, I run a primary education outreach initiative, and I am giving a year 3 talk tomorrow about space junk to about 108-year-olds. So just trying to get them interested in why they should care about the space environment, because they're going to be part of solving the problems that their grown-ups have, created over the last few decades. So Dins and then Stuart, but I don't want to lose, before that, I will just answer Ian Bryson's question. Is there a specific list of SDA interested companies available on the UK Space website? The GNOSIS website doesn't currently allow other members to see other members, which is something that we would hope to redress in the future. But there is an SDA working group on the UK Space Trade Association, and that working group, those members you can reach out to. So yes, there's a group of UK Space Trade Association members who have a specific interest in SDA, and you can contact them. You can contact them also through the co-chairs of that working group, who are Alan Antrobus at Airbus and Mark Cole from CGI. So I would definitely encourage people to have a look at that list of companies. Dins.
Yeah, I just wanted to say, actually, just remind me of one thing I failed to mention, which is the fact that educating others about the significance of space. We work very, very closely with Kilda Observatory, and we're bringing the satellite message to the astronomers, not only of Kilda, but to the entire population of the Northeast that they managed to seem to reach out to. So closer links between the the space operations world and the astronomy world is certainly a welcome thing, and it works very, very well. Instead of the scare stories of, my God, Starlink are blanking out the sky, we're actually educating people on the significance and the importance and how we can sustain space.
Great, thanks, Tins. And Stuart.
I'd just like to sort of endorse Emma's comment about trying to get kids engaged early. But I have to report that when we did try and plug the gap between the GCSE that's available in astronomy and university level astronomy education a few years ago, we did encounter some resistance in some quarters to creating an A level in space science, which was a bit disappointing, I have to say.
Yeah, but never say never, Stuart. Well, I'm going to say, if there are no further questions from the workshop, I'm going to try and get us done on time. I do appreciate everybody, all of the panel members' insights. Thank you for sharing your experiences and your ideas. By all means, come to NORSS events, join. Membership is free. We have a series of events in the diary for the rest of the year. Please, we would welcome your feedback. We try and make sure that we get feedback on all our events so we can continue to improve them. Sign up to our mailing list. And a couple of things to be aware of. I should say the Secure World Foundation Summit is June 22nd and 23rd. That's not on this slide, but that will be it's the 4th summit being held in London this year. GNOSIS is one of the sponsors. That is very much looking at the broader topic of security and sustainability, but there will be some very interesting talks, and you can attend virtually or in person. We will have the space sustainability session at NAM, as Bob mentioned, and then please keep an eye out. We've already issued an invitation for abstracts for our next annual conference, which is going to be at the end of November. And hopefully we will be able to respond to the next ESA ministerial with good news about more opportunities through the European Space Agency funding at that conference, but we'll watch that space. By then, I also hope that SDA study report will hopefully have been published and will trigger some more ideas. I should say in that report, I'm just going to double check. I believe there were 32 industrial entities listed in the annex who had participated in the study alongside the 20 academic institutions. So that that document is a good place to go searching for companies that have an interest in SSA and would no doubt like to work with the astronomical community on that. So, Bob, I will hand the floor back to you, but just to say thanks to all the panelists and thanks to all the workshop participants from me.
Well, indeed, and that's all I will do is just echo that to thank all of our speakers and ask everyone who's been in the meeting if they would fill in our feedback form, and if you aren't already on the email list, then here is how you subscribed onto it. And then I think that's it. Thank you all. It's been an extremely interesting afternoon, and I hope it's inspired interest in the SSA area amongst astronomers, and also help to highlight the areas in which astronomy is able to help in SSA. So thank you all, and that's it. We'll stop.
Thanks, everyone. Have a good evening.
Yes. Bye now.